All right. How about that? We have finally started and forgot to turn on my lights so you can see my ugly face a little bit better. And let's get started. Let's get started. How you all doing? Hello, hello. Let's make a cup of tea. So today is Friday. If I'm not mistaken, today is Friday, and that means today, according to the skidoodle, we're doing a random one-off topic, right? So, and on a random one-off topic, I pick a random topic and stream it for the whole stream. But since it's a flight stream, I don't know, is it even a stream? Am I allowed to call it a stream? Maybe not, I don't know. So yeah. And the topic of today's stream was suggested by Panapudi. I'm pretty sure they actually sent this link in our Discord server. I'm not quite sure. Let me actually see. Can I find that link in there and confirm that it was? Yeah, it was a Panapudi. Yes. MPM fluid simulation. So yeah, the topic of today is material point method for fluid simulations. So this is a very interesting article, and I'm going to put it in description, of course. I'm going to put it in description. So it's going to be there. And I skimmed through the article, and I couldn't understand like a half of it. But I really like the pretty pictures that I'm seeing here. I really like that. And on top of that, there is a source code provided in here, and there's sort of like a guide on how to achieve like similar results. So maybe by having like source code, we can sort of go through it and just understand what each individual part does. Unfortunately, the source code is in C# for Unity. I never programmed in C#. Well, I mean, I programmed in C# once. It was like kind of like some time ago. So I did Advent of Code 2020. Right, and I basically did a challenge where I used different language for each day, including assembly, by the way. Yes, I programmed in assembly and I solved the problem in assembly. How about that? I think there is even a playlist of that. Yeah, I think there's even a playlist. So if you go to the Sojin Woods channel, there's a playlist, Advent of Code 2020. Yeah, here is the playlist. I'm gonna put the playlist in here, Advent of Code 2020. And one of the languages that I used was C#. Yeah. And I programmed in C# on Linux. Yes, I used Mono and stuff like that. So I know a little bit of C#. I mean, if you know how to program in imperative languages, you pretty much know C#, right? So, and I have a lot of experience with Java, and C# is basically Microsoft Java. So anyway, I know a little bit of C#, but I know nothing about Unity. So we'll see how it goes. Maybe this entire idea is going to be a complete goddamn disaster, and in that case, maybe I'm never going to publish it on YouTube. But if you're watching that on YouTube, I guess I'll probably upload it on YouTube even if it's a disaster, because yeah, whatever. It's content. It's fucking content, mate. All right, so I'm gonna go to the kitchen, turn on the kettle, and I'm gonna be back, and we'll think about the plan for today's stream. All right. All right, the first thing we need to decide is what technological stack are we going to use for our application, right? So I don't really know the coordinate system of Unity, but I would presume it's something closer to like OpenGL or something. It's just like, Three-dimensional coordinates and whatnot. Maybe it would make I don't know what I'm talking about. Maybe it would make sense to use OpenGL, right? And on top of that, it would be kind of cool to even color things like in a similar way, and to be able to color this kind of stuff in runtime without any lags. You definitely need to use some sort of hardware acceleration. So OpenGL, we don't really have that much choice in this environment where currently I'm on Linux, except Vulkan, but I don't know Vulkan that much. So yeah, I think the first like part of the stream is gonna be me coding sort of like a application, like a test bench application that is capable of rendering these particles, right? So I want to be able to have a buffer of the particles, right? That I can just, you know, tell my system to render, and it will just render them instantaneously using OpenGL and whatnot. So I'm gonna just quickly set things up. I'm gonna be using my favorite OpenGL template. As you know, OpenGL was never designed to be understood. It was designed to be copy-pasted. So if you program in OpenGL quite often, you probably have a similar template from which you copy-paste initialization of the OpenGL, setting up the VBOs, VAOs, vertex attributes, and stuff like that, you know, because it has a lot of like a lot of code just to do these simple things. So yeah, I'm gonna use my own OpenGL template, and if you're interested in it, I can put it in the description as well. So my OpenGL template. So it's based on GLFW and glue, which is like, you know, GL extension loader or whatnot. And yeah, so I'm gonna quickly code this thing up. I think my tea is ready, so I'm gonna pour myself a cup of water. I still didn't buy a new French press or at least a teapot because I just didn't have time, and I have no idea if I ever will have time. So I'm sticking with the tea bags for now. So yeah, I guess. Rest in peace, French press. Rest in peace. I didn't code that moment live, but at least I caught it on camera. Content, motherfucker. I'm sorry if it took too long traveling with my cow yet again. All right, so let's start sorting. Let's start coding. So let's create maybe some sort of a project. Let's call it npm, and let's create a main application. We're gonna use C this time, right? Because I will have enough trouble trying to understand what the hell is going on in here, so I don't need to use the language for which I have to look up each individual function. And I already have some pieces of code that I can copy paste for C, so it's just like easier to use C for this particular case. Right, it's not like I like C. Actually, I didn't really like C that much, but I like its simplicity. All right, so just a second. Okay, so let's write a hello world because I want to set up the build. Right, we're gonna have make file. We're gonna have make files. npm depends on main.c. Then we're gonna build with cc and c flags. The output of the executable is gonna be npm, and also we're gonna have some libs. Okay. In terms of C flags, we're going to enable all of the warnings, all of the extra warnings. Standard is going to be 11. It's going to be super pedantic. There we go. And in terms of dependencies, we're going to have GLFW and glue. Let me actually open my team mucus. It's going to be sorting npm. There we go. Package config list all. Is it GLFW? Okay, is it independent? I don't remember. Is it? Yeah, it's actually a small case. And what about glue? Not blue. Glue. GLUEU. Okay, all of them are small case, so I might as well introduce a variable that holds all of my package dependencies like GLFW3 and glue, and so I can reuse it in here. So, oh my god, Emacs, C flags, packages, and libs is going to be package config, libs, packages. There we go. So we set up a very simple makefile. Can we build all of that stuff? I think we can. Cool. So if I try to run this entire thing, it says hello world, and I forgot to put a new line at the end of printf. Disgusting. Absolutely disgusting. Am I even a programmer? Am I even a programmer if I make such a stupid small mistakes? I don't know. I don't really know. So the next thing we'll need to do, I suppose, is to create GLFW window. GLFW window. Let me put some salt into my tea. Just stir it up. Just stir it up and enjoy it, I suppose. Disgusting to ASMR. All right, how do you create an GLFW window? So it's located somewhere in main, I suppose. Where is my main program? Come on. Okay, so you initialize GLFW first like this, right? So could not initialize GLFW if it fails, of course. Next thing we create a window. Right, we just create the window. So what we're gonna put in the title, npm, a material point what? Method. I can never remember what npm stands for some reason. It's just like, yeah, material point method. Okay, this is probably because I'm not a physicist. So if I was a physicist, maybe I could remember these kind of things, but I'm not. I'm not. Sorry, I'm just a stupid programmer. Okay. I'm just a stupid programmer. I need things to me being explained an average gopher could understand. Okay, I'm sorry. So let's create the current context. Let's create the current context, and let's initialize the glue. We need to initialize the extension loader. And do we need an instance drawing? I think we do need an instance drawing because I want to be able to just give OpenGL a buffer of points, right? And from each individual point, I want to actually generate some sort of like a square. Right, and to do that, I'll have to have an instance rendering because I want to have like an instance per triangle, right? An instance per triangle. So we definitely need instance drawing. So I'm gonna just check for this specific extension, and yeah. So what else do we enable here? So we also enable debug output. From what I learned, debug output in OpenGL is a must-have thing, right? Because quite often you will make mistakes, and OpenGL knows what kind of mistakes you usually make, so it can warn you about this kind of stuff. So it's quite important to enable it. So another thing we want to enable probably is the blending, alpha blending. And so we also have the different callbacks, especially the callback when the window gets resized. When the window gets resized, we need to reset its viewport. So let me find the function that resets the viewport. Let me grab it from here. So it receives the new size. And just updates the viewport. I think it tries to center it. in a window. So that's precisely what it's doing. As you can see, it just like takes half of the width and subtracts half of the screen, so the actual drawing area is in the center. So that's essentially what it's doing. So let me go back in here. We maintain the time because we constantly pass the time to the shaders usually to animate things, but I'm not sure if in this particular case we're going to be animating things on the GPU. We're going to be primarily doing that on the CPU, though if we were doing compute, right, so with OpenGL or maybe Vulkan or something like that, maybe we could animate these kind of things on GPU. That would be kind of interesting topic on its own. What do you guys think? I haven't done any compute streams ever, I think. At least I can't remember doing anything. I think I tried to do OpenGL, but I think I was planning to do OpenGL, but since I couldn't set it up on my laptop, I decided not to do that, right? So, I don't know. But yeah, maybe if this thing is going to be successful and we manage to have something working on a CPU, maybe at some point we can try to learn about compute, right? And port it on the GPU using OpenGL or CUDA or something like that. I do have an NVIDIA GPU, integrated one, but on my Debian, they don't have a proper drivers, so they work. I don't know, like they claim that they do drivers for this GPU, but I just couldn't set it up and I couldn't bother to do that. So maybe at some point I'll just find motivation to do that and set up NVIDIA drivers and maybe try to do CUDA. And I heard people say that for this particular graphics card, CUDA should work. I don't know. I also heard that CUDA is really annoying to work with. You have to download a shit ton of proprietary stuff and whatnot. Anyway. So let's continue. Alright, so we're organizing the event loop and we're looping until the window should close, and then we're cleaning up the color buffer, right? We're cleaning up the color buffer and we're swapping the buffers and we pull the events, and that should be enough to create a window. I'm pretty sure that should be enough to create a window. All right, so we have a couple of unused things. Okay, so on top of that, I also need to import some of the headers, right? So I need to import GLFW and glue. Otherwise, none of that is going to work. Let's now try to compile this entire stuff so we don't have a screen width. Let's use a very small screen width, like 800 by 600, because why not? Okay, so we have a window. Which is pretty pogue, and let me see if I can actually change anything within that window. For example, the clear color. So GL clear color. I'm gonna try to set it to red. Right, I'm gonna just set it to red. It's gonna be something like that. There we go. And if I try to recompile, there we go, it's red. Okay, comrade. That's pretty pogue, not gonna lie. So we're capable of creating a window and do things within that window. Alright, so now we need to set up shaders. Right. We need to set up shaders. So also I want to use OpenGL 3 shaders with the core profile, and I think this particular OpenGL template doesn't use core profile for some reason, probably because I actually implemented it before I knew how to do that. So I think I can steal that from my latest project for immediate UI, because I remember there I actually set up, Hamikovi actually helped me to set up the profile for this thing. So yeah, essentially before creating a window, you have to add the hints for the window, the version of OpenGL that you want, and what kind of OpenGL profile you want. So you just say you want a version 3.3 and OpenGL profile core. So I can just copy paste this entire thing in here. Before creating a window, we're gonna set it in here, and hopefully that will work, and I will be able to use the latest, not latest, but at least more or less modern shaders. because I think, I don't know what kind of shaders I'm using in the OpenGL template example, right? But, well, I mean, I'm using 3.0, but for embedded systems. So, yeah. It's not that bad, but I mean, could have been a little bit more. So I'm thinking maybe I should actually update the OpenGL template right now, or maybe not. Nah, whatever. Let's do that a little bit later. Let's do that a little bit later. Okay, so we need some shaders. So since OpenGL 3, as far as I know, it cannot work with SphereV. And even if it can, I don't know how to use SphereV. So I'm gonna just store the source code of shaders in the application itself in the form of a string. Okay, so vertex, let's call it vert shader source. Right, it's gonna be vert shader source. The classical thing that I do every time I need to program with OpenGL. Okay, so nothing special, nothing particularly special. Yes, finally, Earl Grey. And a taste of paper. I can still taste the paper. This is my second day of drinking tea. I still can taste it. Maybe at some point I will stop tasting it. Who knows? So the version we're going to be using is 3.3.0 core, and this is going to be a new line. And let's do the following thing. Let's create an empty line in here, so it's easy for me to always like clone it if I want to create a new line. Right, I just don't want to put the shaders into separate files, right? I just want to bake them into the source code. That way your executable doesn't depend on external files, so you don't have to carry them with you and stuff like that. So it's just a little bit easier. It's a little bit inconvenient, but it's not that much inconvenient. It's not that much inconvenient. So I can definitely write a little bit of code inside of a string. It's not that bad. A little bit, but a little bit inconvenient, but not that bad. All right, so in case of a vertex shader, so what we're gonna do in here, I think I'm gonna leave it empty for now. Right, I'm gonna leave it empty for now. And let's create a source code for the fragment shader. So here is the fragment shader. So none of them are correct. Vertex shader is supposed to set up GL position or something, and the fragment one should output some sort of a caller for the fragments. But we just need something to try to compile. And in the source code of OpenGL template, I'm pretty sure we need to grab some things to compile the shader. So, okay, I have a function compile shader source. Let me quickly grab this entire thing. So where I'm gonna put that? I'm gonna put it in here. So compile shaders, shader type, and also we need a way to link the program, right? Because how you compile shaders, you compile each individual kind of shader, vertex shader, fragment shader, maybe geometry shader. I never worked with geometry shaders. Maybe you do with them something different, but I doubt that. And then once you compile them, you link them, just like C source code. You link them together, and then you have a shader program that you can use when you perform draw calls or something like that, right? So, and the reason why you sort of link them separately is, I presume, because some of the shader programs may reuse some of the kinds of shaders. So basically, some programs can share the same kind of shader. So they can share the same vertex shader, right? Because they only need to differ in form of a fragment shader. So that's why you want to sort of link them separately and compile them separately and then link them together, right? So you can have different combinations of fragment, vertex, and geometry shaders, if that makes any sense. Anyway, so let's copy paste this thing in here. So this is going to be link program. Cool. And we have a source code that does all of that. So as already mentioned, OpenGL is not meant to be understood. It's meant to be copy pasted. I'm not quite sure why we're deleting shaders after that, but maybe that's all right. Kind of, maybe that's all right. Who knows? All right, so let me try to compile this in, I think, and see if it works or not. It doesn't work. because it's using Boolean, and to use Boolean in C, you have to include stdbool.h, otherwise it's not working. Okay, and it seems to be working. Cool. So let's try to compile shaders. So here we initialized everything, and I think maybe I have to actually set the size. Well, I mean, resize requires OpenGL initialize, so maybe it makes sense to actually set it after we initialized OpenGL. Okay. Okay, so here what we want to do, we want to load shaders, right? So let's create a special function that's called load shaders, and it's going to be relatively simple, right? What it's going to do, it's going to compile all the shaders, compile shader source like this. So the source is going to be provided through a variable. So here's the shader source, and shader type I think is going to be GL vertex shader, and the compiled shader identifier is going to be returned through the pointer. So we need to have something like GLUint shader vert shader, right? It's going to be initially 0, and we just pass a pointer to this vert shader. There we go. Now, if this entire thing did not compile, we have to crash. Right, as far as I know, the reason the compilation error is actually reported by compiler shader source, so if it failed, I don't really have to print anything, I just have to crash. So it makes it a little bit more convenient for this specific case. Frag shader 0 if compile shader source. So we compiled vertex shader, let's actually compile fragment shader. Frag shader source GL fragment shader frag shader, and we exit this entire stuff. Okay, so we compiled both of these shaders. So once you compiled all of them, you need to link the program, right? So we need to provide the vertex shader, the fragment shader, and the resulting program, right? So this can be like this. Do we really need the resulting program? Right, because we're going to be just compiling it and using it. Does link program automatically use it for you? No, it doesn't use it for you. So one of the things we will have to do in this case is after it's done, we have to use the program, right? So it's going to be something like this. Program, like that, and exit 1. There we go. So we compiled and linked everything, and something exited abnormally. I don't know exactly what. Did it? Excuse me. Did it actually segfault or something? Oh yeah, it has to be the yeah. So I said it to exit when it's successfully linked, right? When like I need an opposite logic. I actually need an opposite logic. Alright, so yeah, now everything works and nothing really fails, except there's a couple of like warnings. I'm not sure if these are warnings, but sometimes it's like a little bit of a noise from the OpenGL login system that doesn't really mean anything, but sometimes it actually says important things. Okay, so we already wrote almost 200 lines of code, and so far we have a window with a black background. So nice job, OpenGL. Okay, so what else we need to do? We initialize the shader, so that means we can execute some code on the GPU side, right? We can execute some code on the GPU side. So I suppose now we need to write some code to initialize the buffers into which we're going to be putting positions of these particles, right? So we need a place for positions of these particles. So far, I think, do we want to? I'm not sure if you heard that, but my neighbors are doing something weird yet again. Something kinky and weird yet again. Do we need to pass the colors? It will be kind of cool to pass the colors, I think. So you can display those colors on the GPU and whatnot. But I'm not sure. I really like these vortexes that form in here. I think it's pretty cool. I'm not sure if we'll be able to simulate that, but we can try to simulate something super simple. Yeah, so there's some examples in there. And what I like, there is a GitHub repo in here. Let me take a look at that GitHub repo. So I'm not sure where to find it. I think it's project settings. No. I know nothing about how Unity projects are structured. So intro single threaded. I cannot see there. Yeah, so there's a couple of extensions. So I think this is the one we need. So I hope this is a complete working example. It looks like it is. And luckily it's not that big. I mean, I just said that we also have almost 200 lines of code, but this example does more than just shows an empty window, okay? So I'm not being hypocrite or anything. Yeah. So this thing is supposed to do more than just show an empty window, and it should be relatively easy to port it, I suppose. Relatively easy. So I suppose from what I skimmed through in the article, the main two things of this simulation is a particle with its position, velocity. So it also have a fine momentum matrix unused in this file. Okay, so maybe we don't need that. Thank you for letting us know. So there is also a mass, and there's also a padding just for performance. Aha. Just for performance. Is it like really unaligned? Well, so you have X and V, right? X and V, and you have two floats. So that means you have 4 floats, and then 8 floats, and then you have... Okay, so this entire thing forms 9 floats, right? So they want you to like pad it with another one just to have 10 floats, I suppose. Or my... yeah, probably that's the reason. Maybe it's better to have even amount of floats, because they sort of maybe stored in memory as pairs because of like vectors or something like that. I don't know how Unity works, but from what I saw in the article, they're actually referring to something like performant. I forgot how it's called. High performance yeah. So here's the thing. I'll be building it out as a single file, examples in Unity, using Unity's data iterating language, high performance C#. Again, I know nothing about Unity, but apparently they have a separate language that is not called C#, but rather high performance C#. Is that a separate language, or is that a subset of C# or something like that? And of course, they had to stick yet another buzzword in here. But yeah, it's kind of interesting. So it's not really C#, it's a high performance C#. What was that supposed to mean? And of course, there's a lot of bullshit videos about that with the bullshit subtitles. I wonder if there's a way to find anything interesting. Is C# a low-level language? Is C# a system language now? Okay. I don't know. I guess. Oh, that's very interesting. Okay, so let's actually read the description. A massive fan, I don't care. I don't want to read that, sorry. Not really interested, not really interesting. Too much text, too much text. Just like this article. So the reason, by the way, why I'm going to be reading the source code instead of like this article is because I just cannot bring myself to read this kind of stuff. Like I just cannot. Like it's super boring. I want something that I can play with, that I can actually run and experiment with, and only then I can understand. There's nothing wrong with these kind of articles. And there's nothing wrong with reading and understanding this kind of articles. It's just like I'm physically incapable of doing that, right? And don't judge me for something that I'm physically incapable of doing that. Otherwise, you're a bad person, okay? So, all right. What I was doing? What I was doing? So, yeah, I wanted to initialize the buffers into which I'm going to be putting my my points that I'm going to be displaying with OpenGL. That's what I wanted to do. So let's create a function called, maybe this one should be called init shaders, because the second function I wanna call is init buffers, right? So maybe for asymmetry, this one should be called init shaders. Init shaders. All right, so init buffers, we don't have that function yet. So it's init shaders, and I'm gonna put it somewhere here. It's gonna be void init shaders. All right. Not shaders, buffers. So how many vertices are we going to have? Vertex attributes. I think we're going to have position first of all, and color, right? So there's also going to be a color of the vertex. So let's introduce some sort of enumeration, maybe. So it's going to be called the trips, and it's my favorite way of like defining the attributes. Just make it a little bit more type safe, maybe. I don't know. So next one is going to be position trip. It's going to be 0. Then we're going to have a color trip. It's going to be color trip, and then we're going to have a thing that tells us how many attributes we have. Count attributes. There we go. So we have all of these things. The next thing we need to do, we need to create the vertex array object. The vertex array object. So OpenGL. I'll need to store the buffers somewhere, right? I'll need to store the identifier of the buffer, and I also need to store the VBOs and stuff like that. But I think I'm gonna actually store everything in a single VBO. I think it's gonna be a little bit easier to work with this kind of stuff. So maybe we're gonna have some sort of a structure. Buffers, I don't know. So, and in here we're gonna have GLU int VAO and VBO. Right, so we're gonna have two vertex attributes, a single buffer within which we store all of these vertex attributes. Initialize the buffers. So how are we gonna return this kind of stuff? So maybe I'm gonna actually return buffers like that, and we're gonna have something like buffers result, and it's gonna be initially 0 initialized, and then I'm gonna return the result like that. Right, in the place where I'm calling init buffers, I'm gonna be actually saving them like this, so it's a little bit easier for me to reuse them and whatnot. To be fair, let's actually put them in the global variables. I think it's going to be easier. We're making like a very small program, so there is no need for like, you know, encapsulation and separation and stuff like that. It's like a very small program. I mean, come on. And it's a throwaway program. It's just a throwaway program. So maybe we're gonna initialize it to 0, so the compiler can put it into a 0 initialized section of the memory. And let's generate arrays, vertex arrays. There we go. Okay. So how many vertex arrays we want to initialize? So only one, to be fair. I don't plan to have like separate of them. Just we need only one. I'm not a greedy person. Just give me one, please. Thank you very much. All right. So after we created it, I think we need to bind. Right. We need to bind. GL bind vertex. Vertex array. I think that's the function we need. Not the function we deserve, but the function we definitely need. Okay. So we're going to be binding this stuff like that. So it's going to be VAO. Bind vertex array. Okay, so everything is created and everything is bound. So the main question that people usually have when they program in OpenGL is what's the difference between VAO and VBO? Well, first one is vertex array object and another one is vertex buffer object. The difference between them is very subtle. I actually talked about the difference between them many times on my streams. Maybe I want to make a video about that, but again, I'm not really good at OpenGL, so I might be actually wrong in terms of what's the difference between them. But as far as I can understand, and quite often the explanations of the difference between them doesn't really make much sense for people who only learn OpenGL. But after some point, after like working with OpenGL long enough, this explanation sort of clicks in your head and that, okay, that makes sense. So the main difference is that vertex buffer object is a place in the memory, right? It's just like a memory buffer, like in terms of bytes, like it's untyped memory buffer. Whether it's typed or non-typed is also questionable because you can have different targets and whatnot. It doesn't matter. It's just details. So it's just like a chunk of memory. It's like an array of bytes, and you can store whatever the hell you want, right? And VAO, if I understand correctly, is a collection of vertex attributes, right? So one is a chunk of memory, another one is a collection of vertex attributes. And this is the best explanation that I can give without going too much into details, because to give more detailed explanation, you have to now understand what is a vertex attribute. Well, it's also a pretty much complicated topic, but the vertex attribute is a single thing that you pass to your shader, right? So the data that your shader, like the vertex shader, accepts, it could accept the data from the uniforms, right? But it also can accept the data from the vertex attributes. Yeah, so VAO is a collection of vertex attributes. So here, for example, I have two vertex attributes, one position, one color, precisely the ones that we will need, by the way, in our example, right? But so yeah, vertex array object describes the collection of those things. And so if you have a shader that accepts different combination of vertex attributes, you will need a different vertex array object for it. Right. It's sort of like a collection of vertex attributes is sort of like a schema of the data, right? It's a schema. What kind of things your shader may accept, right? And it describes the schema of the data that is stored in VBO, right? Vertex buffer object is sort of like a place, like it's just data, just raw data. And vertex array object is a collection of vertex attributes, and vertex attributes is basically explain how to interpret that data in the VPO. Again, if you never work with OpenGL, none of that makes any fucking sense, right? But if you worked with OpenGL long enough, if you copy-pasted the same examples over and over again multiple times, or at least retyped them, trying to understand them, if you went through a lot of tutorials, after some time, this explanation sort of clicks. So yeah. And this is another reason why I don't want to make the video about difference between VBO and VAO, because it's probably not going to help you. I suppose it's a similar like trying to explain what is a monad, right? So in pure functional programming, there's a thing like a monad, and it's pointless to explain it. There's so many articles trying to explain what is a monad. None of them explain anything. It's just like something that you have to understand yourself. Like at some point where if you've done enough Haskell or enough pure functional programming, it will just basically click in your head. Right, so yeah, it's one of those things, I suppose. You can try to explain it, you can try to understand it, but just need to give it some times. Right, to understand some things, you just need to give them some time, right? If you don't understand something, maybe the time has not come yet. Maybe. All right. Just gonna be sipping my tea. All right, so what were we doing, by the way? I think we were setting up VAOs and VBOs. That's what we were doing. I also need to set up some memory on CPU to store my points, so from that memory I can basically copy to the GPU memory. Right. So let's define something like vertex, I suppose. Let's define a structure called vertex. Right, so this is going to be a vertex. And a vertex is going to consist of things like float x and float y for the position of the particle, right? And then we can have some colors, I suppose, something like R, G, B. And we need A. Do we need transparency? I suppose for now we don't really need. any transparency. So I'm just gonna leave it like this. I'm gonna just leave it like this. So this is gonna be our vertex. So then maybe we can define some sort of a buffer in here, the buffer of vertices. Thank you very much, English, for not making the plural of vertex just vertexes. Well, I mean, doesn't really work. That's probably why the plural of vertex is actually so different, because as putting s at the end of the x doesn't really work. That's probably why. Okay. Why not vertexen then? I don't know. Whatever. Vertices capacity. We're gonna have some sort of vertices capacity, and how many vertices do we want to have in here? Vertices capacity. Let's actually allocate 1024, not 100. So, and also let's have some sort of a variable that keeps track of how many vertices we already have in there. So it's going to be vertices, vertices count. I have an idea. What if we rename vertex to just vert, and the plural of vert is going to be verts. I think it's a good idea. Yes. And it's also less things to type. Okay, so just less things to type. All right, so here is my buffer, memory buffer, into which I'm going to put in the vertices, and then sending that buffer to the GPU, and then the shader is going to process that buffer and, you know, display all of that stuff, display all of that jazz. Okay. So the next thing I need to do, I need to create a buffer. GL, again, buffer, vertex, VBO. I need to create VBO. Excuse me. All right, so I want to create only a single buffer in here, right? I'm going to be creating only a single buffer, and this one is going to be VBO. So we just generated buffer. Then we're going to bind that single buffer, and after we bound the buffer, we need to initialize the size of the buffer. The size of the buffer is usually initialized with GL buffer data. I think that's how it's called. I'm pretty sure. Let's go. Ever. Okay. So the target in our case is going to be GL array buffer, right? So what's the size? I don't remember what's the size. Specify the size in bytes of the buffer object's new data store. Well, that's easy. So the size is the size of this entire array. So, and actually the C allows us to just get the size of this thing. I personally find this like size of array the most confusing feature. Especially considering how arrays, when they're passed to a different functions, decay to a pointer, and it's such a huge minefield. And I definitely stepped on some of the mines in that minefield. It's just like, oh my god. Right, so the thing I'm talking about is that, okay, you have an array of numbers, right? So you have 10 of them. So, and if you try to print the size of that array, it's going to be ZU, size of access, right, there we go, you need something like include stdio.h and stdlib and stuff like that. If you try to compile this entire thing, it's going to be foo C, and if you run C, and there we go, you got 40, which is kind of weird if you're only starting to learn C, right? If you look at this kind of example from the perspective of a complete newbie, right? So size of access is 40, and it's like, why is it 40? It has to be 10, isn't it? Well, it's size of array in bytes. Ah, it's in bytes. So then to get the amount of elements in here, you have to get the size of the single element, like, and divide the whole size by that element, and only then you get the size of the array, right? And then, okay, so what if I want to pass this entire thing to a separate function, right? So I'm just passing it like that, right? And essentially, I might as well actually use the same name, right? So everything like this works. You get 10, right? And then you just move the same piece of code to a different context, right? To a different context. And you just pass the array like that. And well, at least it sends a warning. But some of the compilers may not send you a warning, but the output value is completely different. And it actually means a completely different thing. So the same piece of code in one context means one thing, in another one it means completely different thing, even though the target types of the variables we're talking about are like syntactically the same. They're syntactically the same, but they're semantically not. And it's just like, holy shit. Ah! Thank you, C. Very cool. Anyways. But Zozin, what do you think about Rust? Okay. So the next thing in here is actually data, right? We need to send the data in here. So we provided the size, and now we provide the data, and the usage is going to be, I guess the usage is going to be dynamic draw, because we're going to be constantly, first of all, we're going to be drawing from this thing. I suppose that's what draw stands for in here. Maybe it stands for something else, but I'm going to just assume that it stands for that. And we're going to be constantly updating that buffer dynamically. Yesu, 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 kawaii fucking desu. Here's the buffer data. Do I need to do anything else? So I created VAO. I created. Oh, now I need to initialize the vertex. Yeah. Force NCD. So we need to use this weird function GL enable vertex attribute something. I don't remember. I think that's how it's called. I'm gonna just assume that's how it's called. So enable or disable generic vertex attribute. Just to be sure, I think I'm gonna just look at some of my examples. GL enable vertex. I don't even have that. Oh, because I don't even use the vertices in here. Okay, so I need to take a look at my other example, like for immediate GUI or whatnot. For immediate GUI, because I'm pretty sure I use that thing there. Yeah, enable vertex attribute array. So I think I guessed this function correctly. I almost know OpenGL by heart, at least some of parts of the OpenGL. Okay. So what we enable? We need to enable the position attribute, I suppose. Right. So this is going to be position attribute. After we enable that specific attribute, right? After we Emacs. After we do that, we need to call to a different function. GL vertex something pointer, right? GL vertex something. No, not that one. GL vertex. Oh, I think I saw it. Attrib pointer. Yes, I found it. Yes. Yes. Okay. Oh boy, where is my soy? Okay, so position attribute. The size, let's take a look at the size. Specifies the number of the components per generic vertex attribute. So yeah, you can only send like 1, 2, 3, or 4 floats, and the reason is because of the types of the shader. Like on the shader, you can work with types like float, vec2, which is 2 floats, vec3, which is 3 floats, or vec4, which is 4 floats. That's why the size is 1, 2, 3, 4, right? If you need to send like a bigger things, you can split them into smaller vertices, I suppose. And I suppose you cannot use like matrices as a vertex input too. So in our case, the size of the position, so it's like a 2-dimensional vector, so we're gonna just put 2 in there. Why not? So the type specifies the data type of each component of the array, symbolic constants. In our case, that's a GL float, and this is what I find confusing about vertex attribute pointer, is that you cannot use GL unsigned int or GL bind. You have to use a completely different function. But what's interesting, I suppose if you provide the GL unsigned int, what it will do is it will reinterpret the bits of unsigned int as float. I guess that's what it will try to do, and that's the point. So basically you can store floats in ints just to have a full access to its bits for some sort of like a IEEE 754 black magic or whatnot. I don't even know why would you want to do that. I'm not a computer graphics engineer, but computer graphics engineer are wizards, that's for sure. So anyway. So the next thing, yeah, already specified that. Next thing we need to specify whether it's normalized or converted directly as a fixed point values when they're accessed. I always put like false in there, so I guess I'm working with the fixed point numbers. Stride. Okay, stride is interesting. Specify the byte offset between consecutive generic attributes. Stride 0 is the generic attributes understood to be tightly packed in the array. The initial value is 0. Oh, okay. So essentially, we store both of the attributes in a single structure. So this array of attributes, we actually store two vertex attributes in parallel in a single array. So the first vertex attribute is this. The second one is this, right? So this is the position attribute, and this one is the color attribute. And as you can see, we sort of store them in the same array. So to tell that to the OpenGL, we have to provide it a stride. Stride is the size of the whole sort of component in here. Right. So essentially, the OpenGL will receive your buffer. Let me actually try to draw that. It will receive the buffer. All right. Receive the buffer, and then within that buffer, first two things are going to be position x, y, and then the second three things are going to be RGB, right? So RGB, and so on and so forth. Right. It's not straight. X, Y, R, G, B, and so on and so forth. So each sort of component is that. So basically a sequence of X's, right, and so on and so forth is position attribute, position vertex attribute, and sequence of RGBs is the color vertex attribute. Right. For OpenGL to know that it needs to skip this color to find the next position attribute, we need to tell OpenGL the size of the whole of this chunk. And the size of this whole chunk is the size of the vertex structure that we just defined, right? So the size of this entire thing. That's basically why we need to define a stride. And stride is essentially the size of this entire thing. It's the stride, right? So that's basically what we're describing to OpenGL. All right. GL vertex attribute stride is going to be size of vert, and this pointer, as far as I know, is an offset, right? Offset. An offset is precisely offset within the stride, right? Offset within the stride. So for the vertex attribute, the offset is going to be 0 because you basically step by stride and you offset with 0 and you get the entire thing in here. Right, you get the entire thing in here. And the size of this entire thing, by the way, is determined by the size attribute, you know, the one that can only be 1, 2, 3, and 4, right? So it knows that it's 2 of them, it knows that they're floats 32-bit numbers, so it knows precisely the size of this component, so it doesn't need any additional information. All right, and what's interesting is that offset is a pointer type. But it doesn't mean the absolute pointer in your memory, in the memory of your machine. No, it means the relative offset from the beginning of that vertex element. Right. I have no idea why they accept it as a pointer, which makes it look like it's an absolute position somewhere in the memory of your machine, when in fact it's a relative position. Maybe legacy. This kind of stuff usually is explained with, yeah, legacy, sorry. So OpenGL has a lot of very, very old legacy stuff that needs to be maintained. Maybe not, I don't know. Okay. So, and in our case, yet again, we're going to do GL void 0, so that's the offset, and we successfully initialized a single vertex attribute, the position one. So we told OpenGL how to find this XY, XY. All right. So next thing we need to do, we need to enable color attribute, right? We need to enable color attribute. So, and yet again, let's copy paste this entire signature. And index is going to be the color attribute. This is the color attribute. The size, it's 1, 2, 3, or 4. The color has 3 components, RGB, so we're going to say it's 3. The type is GL float. It's not going to be normalized, I don't remember what it is. So I'm going to just say GL false. The stride is the same because the color attribute is stored within the same structure, so the stride is going to be the same, but it's offset. It's offset by 2 floats, right? It's offset by 2 floats, first one and second one. Maybe that's precisely what we're going to say in here, I don't know. So size of a single GL float, right? It's a single GL float multiplied by 2, right? And of course, you probably need to cast this entire thing to GL void, right? But again, it doesn't mean some sort of absolute memory in your machine. It's just a relative offset within that single component that we're sending in there, right? And there we go. And I don't know, maybe to be a little bit more precise, we want to actually replace these things with GL float, right? So because we're talking about that. And okay, I think we initialized everything. Let's try to compile this entire thing and see if it's going to compile or not, or some stuff like that. So vertices capacity, I forgot to rename it. There we go. Oh yeah, when we're binding the buffer, we also have to specify its target, right? It has to be GL array buffer, and there we go. It seems to be working. Let's actually try to see if it throws any errors in the runtime. And the runtime is absolutely clean, as you can see. It didn't even print anything, so I think we initialized everything correctly. Do we even call this function? Maybe the reason why it initialized so well is because we don't call it, but we in fact call it, so everything's fine. Everything's fine. Okay, so when we do that, we use the program, everything seems to be okay. But now we need to actually put something into the shaders, right? So we compile the shaders, we initialize the buffer. Now we need to actually send the data to the, yeah, we still need to send some data to the GPU. So there's like a couple of things that we need to implement. Let me actually outline them somewhere. Okay, sync the VBO buffers, right? So essentially from time to time, we're going to be pushing new vertices into this buffer, and we need a way to sort of synchronize this buffer with the GPU so the GPU has the new data to draw. Right, so we need to implement that. And on top of that, another thing that is still left is process the data in the shaders, right? Because right now shaders, as you can see, they're empty programs. They don't do anything, right? So we need an ability to constantly send the data for the shaders to consume, and we need to consume them on the shaders, right? And to set up these kind of things where you have a buffer on the CPU and then you can send that buffer to the GPU, and you have a program on the GPU that processes that buffer, you need 246 lines of code. Classic. Okay. So, and I spent 1 hour actually, copy pasting. I didn't even write it from scratch. Like I primarily copy pasted it, but some of the things I actually wrote from scratch. But yeah. But I mean, Vulkan is even worse, right? So if you take a look at Vulkan triangle example, there's even like a short version of the triangle example, like Vulkan single function triangle example. Yeah, I found it on Reddit. This is actually a pretty cool example. Yeah, it's not really the goal of this example was not to be short, but the goal was to be linear, right? So basically, it doesn't introduce any nonlinear abstraction. You can read this entire example from top to bottom and understand how the triangle is created. And this is just a single triangle, and it takes 100 and 300, 1300s. I'm sorry, English is not my first language, so and this arrays of bytes is actually very interesting. It's shaders, but compiled into SPIR-V bytecode, SPIR-V intermediate representation. So yeah, so one cool thing about Vulkan is that you can actually pre-compile shaders and just put them in a binary array and put them into, like, bake them into your program, which is kind of cool. Because in OpenGL and in old versions of OpenGL, you have no choice but store the source code of the shader and compile the shader at runtime, right? You literally, for quite some time in OpenGL, you didn't have an option to precompile your shaders, right? You always have to compile them at runtime. I think on OpenGL 4, you also have an option to precompile them with SPIR-V or something like that. So it actually gives me an interesting idea. Maybe I should make like a Friday stream on SPIR-V and learn how to use it. I'm not even sure if I pronounced it correctly. Is it supposed to be pronounced like SPIR-V or as the SPIR-5? I don't know. Single function example. Vulkan triangle single function example. I'm gonna leave it here just for you. Just for you. Okay. Cool. So we have these things left, right? We only have these things left. So I already spent 1 hour doing that. Am I gonna go to... Okay. So I'm gonna leave a timestamp in the description on how to skip the entire OpenGL setup, so you can skip straight into me trying to implement that or trying to understand this entire thing. So yeah, it's kind of cool, like the power of offline streams. You can always skip some things. But only if I give you the timestamp, otherwise you won't be able to do that. Anyway, so before I finish the implementation of this entire things, I think I want to make a small break and yeah, the usual stuff. So you guys want to listen to some music while I'm peeing? Some jazz? Do you like jazz? Maybe? Some smooth jazz? What? 3 minutes. Let's make a small break. Let's make a small break, and you guys have fun. Yo. Perfect timing, by the way. Not even edited. Dab. Somebody kill me already, please. We're back. Let me make a cup of tea. I already put my kettle on, so I'm just waiting until it boils up some water for my tea. So we need to be able to sync the VBO buffers. So we're gonna syncing them up with GL buffer subdata, right? GL buffer subdata. Right, so I can provide the buffer, right? The target rather, the offset and the size, and yeah, just the data that I want to send to the OpenGL, to the GPU, and stuff like that. It's gonna be super fun when I'm finished initializing everything and doing stuff. It's just simply not gonna work. Because it's usually like that, right? And it's going to be a black screen, no error messages, and yeah. And render doc doesn't really work on my machine. So anyway, my tea is ready. I'm going to go to the kitchen, pour myself a cup of water, and I'm going to be back. All right. Okay. Copy paste time. So maybe I'm gonna create a function literally called sync buffers. That's quite a good idea. Sync buffers. So we're gonna bind buffer GL array buffer. I think that's what it's called, GL array buffer. That's what we're binding in here. That's what we're binding in here, and then we're just calling buffer subdata. Buffer subdata. So the target is yet again GL array buffer. The offset specifies the offset into the buffer's object data store when data replaced will begin measure in bytes. I think we don't want to do anything like that. So the size, specify the size of the buffer in bytes. Okay, so we know how much this buffer is filled because of this variable, but this variable actually stores the size of the buffer in elements rather than bytes. So we'll have to convert elements to bytes. So it's going to be verts count. Verts count. It's a little bit cold in here. My feet are cold. I need to put on my socks. Just a second. Programming socks. Yo, I'm back. Too bad. So we need to convert amount of elements to the amount of bytes. That's to do that, we take amount of elements and multiply it by the size of a single element in bytes. Size of vertex. Maybe we can do something like verts 0 because it's a little bit better. You know why it's a little bit better? Because if you use verts, right, and then in the future you change the name of the, actually not the name, but the type of this buffer, you may forget to change the original size of vert. Right. And I just realized that I fucked up. Well, I mean, that's a good point, actually. So in the vertex attribute point, I actually still used this thing, but that doesn't contradict to my point. I still think it's bad, and that's why I have to change it. I have to change it to vert 0, right? Because again, if you change the type of this element and you depend on a specific type, but not on the element, your program might break, and the compiler won't tell you, right? And you won't know, and you will have weird bugs and stuff like that, right? And you will have like, you'll spend a lot of time troubleshooting, like what's wrong, right? Since this function call semantically expects the size of the element of the verts, let's take the size of the element of the verts rather than its current type, because its current type is something that can change. But semantic of this call is not going to change. The semantic of this call always expects the size of that element. Right, you see? So we sort of like, the type of the element and the element itself, semantically they decoupled, and it's wrong to depend on the size of the type of the element rather than the size of the element itself. Does it make any sense? It makes sense in my head because I drank a lot of tea, but anyway. Doing things like that actually saved me a lot of troubleshooting time, a lot of debugging time. Okay, size of verts, and this is precisely what I want to do here. I'm going to do verts 0, and the data that we're sending there, we're sending verts. That's what we're doing. We're sending verts. Okay, so I need to check if this entire stuff compiles. So we sync in buffers. Also, before binding the buffer, I think it would make sense to actually bind vertex array just in case. Oh, also I forgot the VBO, of course. This one is VAO. I have to bind everything before I actually can use all of that because it's OpenGL. Of course. Make -b, and there we go. And it seems to be compiling. Does it even do what I think it does? Let's introduce compilation error. Okay, so it's yeah, because I cannot believe that I made it first try. Okay. Oh boy, oh boy. So now we know how to synchronize the buffers. Maybe we can also... I also want to have something like clear buffers, which is going to be just doing verts count 0, and there we go, your buffer is clean. And we also need another function, something like push vert, and we'll accept x, y, r, g, and b. Right. It will construct a vertex out of that. Maybe we're gonna do it like this: verts count. All right, and it's gonna be x, y, yeah, r, g, b. Right, and I'm gonna put it like that. Emacs magic, where are you? Boom. Can your Vim do that? It can, I know. Don't tell me anything. Don't at me. I know what it can. Because I also use Vim. Not everybody knows that, but I also use Vim from time to time. Right. And I know that in Vim you can do shit like that. Right? You can just do I think, yeah. So see. How do you do, fellow Vimmers? How do you do? So push the vertex. Also, it's quite important to not overflow your buffers. Man, it's been 3-4 days. I know. But unfortunately, I'm on the break. I need to mentally recover from mental abuse from chat. Nobody mentally abused me in the chat. It's just like it's me who pushed myself too hard and streamed every day and kept exposing myself to all of that stuff on the internet. So it's totally my fault. But it is what it is. And it isn't what it isn't. So see you in a month. So I started my break on when? When did I start my break? Let me see. I think I started it on Wednesday, May 12th. So I guess it's gonna be a month, right? At least a month. I guess the next actual stream is gonna be June 12th, right? Okay, so see you in June 12th. In the meantime, I'm gonna be doing these offline streams. So yeah, it is what it is, and it isn't what it isn't. All right. All right. Okay. Didn't even work properly. Not in a structure union. Oh yes. You see what I'm talking about? I changed the type of the element. Yeah, it is supposed to be vert. Okay. So yeah, there we go. It works. Still doesn't show anything. Like we keep writing code and there's no result. So maybe using OpenGL was a bad idea. But yeah. Anyway. We'll see. We'll see. All right. So we can initialize the buffers. Okay. And at the beginning of this entire thing, what I want to do, right? I want to clear the buffers, right? I want to clear the buffers. Then I'm going to be pushing a bunch of vertices, right? It's going to be something like a 0, 0, and the color that I'm going to be using there is going to be red, right? So it's going to be red, and I'm going to push a bunch of vertices like 10, 10, 20, 20. But if it's going to be in a normalized device coordinates, right? Maybe it would make sense to actually use different numbers in here, otherwise we won't be able to see all of that. But anyway, so sync buffers. I just got a very interesting idea. Let's rename this function to begin verts, right? Sync function to end verts, right? And push vert is I don't know, maybe just vert. I don't know, maybe just vert. And now here we're gonna have begin buffers, begin verts, right? So begin verts. Then we're gonna have a single vert in here, and then we're going to have end verts. Right? You just spelled that correctly. Yeah. So begin verts and end verts. And now we've got OpenGL 1.0. You know, with immediate drawing API and stuff like that. OpenGL 1.0 immediate mode. So essentially we had a retained mode, OpenGL, and we converted it to immediate mode. I think I'm having like some sort of like immediate mode week, right? So everything is immediate mode. Yeah, in all the versions of OpenGL, you're supposed to draw like that, right? You start your triangles, you specify the colors and the vertices of the triangles, and you end. And yeah, that's precisely what I did here. Okay. So I guess that makes sense, maybe. Okay, so, and after this step, we accumulated some vertices, and now we need to render them, right? We need to render them. So we're gonna render them with instanced drawing. So let me see, where is the instanced drawing? So docs.jl. Draw arrays instance. It requires GL3, and that's precisely why we wanted to have this extension for drawing instance array, right? So where's the extension? Yeah, here is the extension. Yes, yes, yes. So what are we going to be drawing? What are we going to be drawing? So basically, I'm going to draw each individual particle as a quad, right? I'm going to draw each individual particle as a quad. The simplest way to draw a quad is to actually draw 4 vertices as triangle strip, right? So OpenGL triangle strip. There's a special mode of drawing in OpenGL that lets you specify like minimal amount of vertices and get a triangle strip, right? Essentially, yeah, for a quad, you just need to specify 4 vertices, and it will basically connect them together into 2 triangles, so you don't have to do anything. And what's cool is that we can basically render only 4 vertices without sending any information about position of the vertices to the shader, and use GL vertex ID to generate those vertices. GL vertex ID. So GL vertex ID basically a number. It's basically a number of the vertex, right? So essentially, if you have 4 vertices, their numbers are going to be 1, 0, 1, 2, 3, right? And if you convert them to binary code, it's going to be 0, 0, 0, 1, 1, 0, 1, 1. And if you use each individual bit here as the coordinate, you get precisely the triangle strip that you need for a single quad. Look, 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 look. Right, 0, 0 is located in here. 0, 1 is located in here, right? So this is 1. 1, 0 is located in here. So you already drew a triangle, and 1, 1 is located in here. So it's actually a triangle strip on the side, but that's beside the point, right? So basically you can just get a number, you just get a number of the vertex, and through bit operation convert it into coordinates of the quad. So you do not need to send any information to the GPU, you only need to know the number of the vertex, and you can just convert it like that quite easily. All right, so you don't need any of this stuff, and that's precisely what we're going to be doing that, and we're going to be using in the instance drawing, right? So each individual particle is going to be instance, and within that instance we're going to run a shader that generates a strip, right, to represent the particle, right? So this is basically how it's going to go. So for each instance it's going to be a program that generates 4 vertices, for triangle strip, and so on and so forth, right? And that's how we're going to get a lot of particles. We're also going to use the positions to offset these meshes that we're generating, and we're also going to use the color attribute to color this entire stuff. And what's cool is that since it's a quad, I can maybe send some information about UV coordinates of that quad to the fragment shader, and maybe we can generate a custom texture here, maybe in a form of a circle or something like that. There's so many possibilities we have. It's just like insane. My God, the possibilities are unlimited. Only your imagination. Only the sky is the limit, right? So I think that's the saying. That's the saying. Only sky is the limit. Okay. So what we're gonna have in here, I suppose, is gonna be GL, but interestingly enough, if I'm having strips, oh yeah, so I have to just use GL triangle strip. So the first one is going to be 0, we don't have to do anything in here, and the count is amount of vertices that we need to draw. Is going to be 4 of them, but the prim count, as far as I know, is the amount of instances, and the amount of instances is the verts count, right? It's going to be verts count. So there we go. As far as I know, that may result in a, it didn't result in a segfault, which is already kind of nice. which is already kind of nice. Did I recompile even everything? Because sometimes it likes to segfold if I'm not putting like ext or something like that in here. It works with and without ext. Though without ext, it was actually complaining about something. It just randomly complains. Anyway. Okay, cool. We synchronized the buffers, and now we need to process the data on the shaders. That's what we need to do in here. That's what we need to do. Maybe before we can process data on the shaders, we're gonna do something. Yeah, let's actually try to draw that quad just to see if it's if our entire OpenGL pipeline is working correctly. Right. So let's just try to see that. So we're gonna just do GL draw arrays. GL, so it's gonna be docs JL. GL draw arrays. So yeah, that's what we need in here. That's what we need. So GL draw arrays. So it's gonna be GL triangle strip. GL triangle strip. The first is going to be 0. The count is going to be 4. Right, and that's what we have in here. So we're just drawing 4 vertices. Just drawing 4 vertices, mate. So okay. We have GL cell mode. We have GL vertex ID. Right. So to get its bits as coordinates, we need to extract them. So let's extract the first bit, right? So this is going to be your x, right? So this is your x. So is this really GLSL? It doesn't look like GLSL, doesn't even highlight it. Okay. So your y is going to be basically this thing shifted to the right, right? So here's the x and y. On top of that, I want to probably convert them to floats. Right, here they are. Here are the floats now. But here's the problem. They are from 0 to 1, right? And the normalized device coordinate are from -1 to 1. So to fix that, we can multiply them by 2, right? So if you multiply this thing by 2, you get from 0 to 2. And after that, you can subtract 1 from all of them, and it's going to be from -1 to 1. That's how you convert the coordinates from 0 to 1 to coordinates from -1 to 1, right? You multiply by 2, 0 by 2 is going to be 0, and this one is going to be 2. And you subtract 1, this is going to be -1, this is going to be 1. Easy! Easy peasy, lemon squeezy. Okay, so, and this one is going to be the same, right? -1. And there you go. Here you have the coordinates. You can put them into something like vec4. So this is going to be your x. This is going to be your y. Z is going to be 0 and w is going to be 1. And this is going to be your GL position. So this is your GL position, and there we go. You implemented a simple vertex shader that generates the strip quad. It's like a strip club, but a strip quad. So how can we convert that to a string now? Well, I suppose, can we have like a special command that basically takes the entire thing, right, and replaces it with that, like that. Boom. I'm an idiot. Okay, one more time. Well, I mean, I had to capture it. I'm sorry, I forgot to capture the entire thing. Now it's a shader. Epic. That's actually pretty cool. So yeah, I need a command that can basically shade, like stringify and unstringify this entire stuff. It's relatively simple. It's just a substitution with a regular expression, I suppose. Right. So my substitution to stringify and to unstringify is actually something like this. Right. Maybe I can put it into here, like that. And so query replace string. Is it query replace regex? Yeah. So what's the function? So it accepts, yeah, it basically accepts the string and regex. So can I just do something like that? I wonder. I think I should be able to. I wonder if it's gonna work. There. There. So let's create a function. GLSL stringify, and this entire thing is going to be interactive, right? And let's compile this function and let's see. So I'm going to try to do GLSL stringify. Easy. What about unstringify? GLSL unstringify. It's going to be interactive, right? I'm going to take this entire thing and I'm going to put it the other way around. I suppose we're going to just match this stuff. Yeah, we're going to match these things. It's kind of interesting. I cannot just... Thank you. Very cool. So the paraded mode is trying to be super smart, right? And it doesn't let me insert the double quote in here. It thinks I just want to type this double quote and just moves it to the right. I cannot just type double quote in here. I can type it somewhere, like I can put a space and type it in here and then remove the space. It's when the software is trying to be smart. Like, why software isn't even trying to be smart? Like, every time software trying to be smart, it's just like, it's not. Like, god damn. I don't know. All right, so here's that, and we're gonna put something like this in here, and it's gonna be just n, and I guess that works now. I guess that works now. So we're doing that, and what I want to replace it with, I want to just replace it with 1. Simple as that. Okay, so now we have an unstringify, right? So we have an unstringify, and can I do unstringify? Yeah, I have to do that here. Oh shit. Okay. Wait, what? Ah, because I have to. Okay, I see. I need to disable paraded smartness. Uh-huh. 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 Ah, this is because I actually have to... No! Maybe I have to put like a new line in here for it to... Unstringify is actually more difficult than I thought. Why does it put that slash in there? I cannot understand. So you have this thing in here. Maybe you don't... Alright, then you capture everything within that thing. And this entire thing also is incorrect, because you also have a comma, have to have comma. Right, so let's go back completely. So it's gonna be something like that. Stringify, yes, and you probably have to do it like that. Yeah. Yep. And in here, you also have that, and you have to have a comma, but I'm not sure if the comma has to be also escaped. Sure, if the comma also has to be escaped, and is it even worth it? I don't think it's worth it. Like, but maybe I can finish it. Maybe I can finish it. So we can stringify, and when I'm trying to unstringify, it doesn't work. Okay. So we have a double quote. You capture everything. Maybe it has to be like sort of like greedy, not greedy, something, I don't know. And then this thing, and then that thing. Yeah, let's recompile this entire thing, and stringify, unstringify, and it still puts that. You know what? I really don't care. Like, it's just like, I thought if I can quickly do that, and I cannot quickly do that, and I really don't care. All right, I'm sorry. I'm sorry. All right. I'm pretty sure it's gonna be shit ton of comments telling me, it's that. You have to fix that. You have to. No. It's. I just wanted to quickly see if I can do that. If I can quickly do that. Don't tell me anything about it, please. All right, so it doesn't matter. It doesn't matter. Okay, it doesn't matter. Whew. All right, so okay, so what I wanted to do, right? I just wanted to again stringify it. Right, I'll just put it here. All right, so now we're gonna put that. So this is the empty string. 1, 2, 3, 4. Right. Do we need anything else? So it's going to be GL position. Okay, so we're generating this thing. After we generated this entire thing, I think we need to do something like GL frag color, and I think it's not going to work, right? Because you're supposed to put like an output to your shader, right? You're supposed to put an output to your shader. So let's actually make it like a red one, right? It's going to be a red one. All right. And oh yeah, you don't have to put commas in here because it's a single string literal. Yeah, there we go. Okay, it works. Nice. I don't need to have an output there. I can now try to do different things. For example, I can multiply this entire stuff. I can multiply this entire stuff by like half. Right, I can multiply it by half. Right, and now it's small, so as you can see, we're like generating this quad on GLSL, right? We're just generating this quad. I'm pretty sure somebody will spend like several hours like trying to research what exactly went wrong when I was writing stringify and stringify, and it will like write a huge comment in the comment section explaining like in details why it was wrong without like disregarding everything I've done in the video, right? So that small little fucking thing, like, yeah, that's the problem in this regular expression, you have to fix that. Fuck everything you did in the video, right? It's just like regular expression, you have to fix it, Zozin. That's why it didn't work. It's very important. Fucking Twitch PTSD, holy shit. Okay, what I was doing, so we can generate this mesh, right? We can generate this mesh. So now I want to actually do the instance drawing, right? So I want to do the instance drawing. For the instance drawing, I need to accept the vertex attributes. Right, so we're accepting vertex attributes. Let me actually go to my immediate UI. Is that the right? Okay, what the fuck am I looking at? Where is the shaders? Where is the shaders? I don't see the shaders. Ah, it's a wrong thing. I should actually look at main.c. Yeah, this is how we do that. All right. This is how we do that. So this is going to be the position. This is going to be the color. In our case, color is actually a three-dimensional vector, right? It is a three-dimensional one. And yeah, that's it pretty much. Oh, and I do remember when you are creating the vertex attributes, right? You're creating vertex attributes. You have to mark them as being instance. You have to specify the divisor or something like that. Yeah, otherwise they're not gonna instance properly. So GL something the vertex. Vertex binding divisor. Is it what it is? Vertex attribute divisor. Yes. That's what I needed. And it's probably yet another extension. I do vaguely remember that. Yeah, I do vaguely remember that. It's yet another extension. It's yet another extension. So let me see. Let me just try to use this entire stuff. Right. So, and the index specifies the position attribute, and number of the instances that will pass between updates of the generic attribute at slot index. Number of instances that will pass. I think you have to put like 1, right? Modifies the rate at which generic vertex attributes advance when rendering multiple instances of a primitive in a single draw call. Or divisor 0, the attributes at slot index advance 1 per vertex. Is non-zero, the attribute advance per divisor instances of sets. Okay, I see. All right, so I think we need to set them to 1 in our particular case. So it's going to be called attribute 1. Color attribute 1, okay. So now we need to do this thing. We're gonna draw triangle strips, but with this amount of things. So the thing here is now, we need to offset each individual instance in here by the corresponding position. So it's gonna be position X, and this one is going to be position Y. But since we're not converting like sort of screen coordinates to normalized device coordinates or anything like that, we will need to use better coordinates in here. So let's actually put something at 0, right? So this is going to be something at 0. This one is going to be at 0, 5, 0, 5, and this one is going to be at minus 0, 5 at and also minus 0, 5. And let's enjoy the black screen. I was expecting to see a black screen, but apparently it worked first try. So each individual thing in here is essentially the particle. We have 3 particles in here. We have now 3 particles. We don't take into account their colors, but we could. We could take into account their colors. So, but we need to pass the color to the fragment shader so the fragment shader can set it up, right? So that means we have to do something like out vec3. So particle color, right? So this is going to be the output. This is going to be the output, and 1, 2, 3, 4. So particle color is going to be equal to the color that we got from here, and then we need to accept this thing in here. So it's going to be in vec3 particle color, right? And we can just use this particle color in here, right? Particle color. There we go. So now. So we use red colors in here, so let's actually try to set different colors. So this is going to be that, this is going to be that, and this is going to be that. I really want to like align this thing a little bit. All right, so let me see, and it failed. It actually failed compiling the shader. That's very interesting. So where exactly it failed? So it's a vertex shader at position like 6 or something. So it's somewhere here. It's because of the A. I see. Okay, so now we have particles of different colors. They don't really look like particles, but I mean, they just have to be a little bit smaller. I'm just thinking, do we have to like use screen coordinates or something? That would be actually kind of nice to use screen coordinates. Yeah, because it will simplify a lot of things. Okay, just a second. I need to take a look at it. I've got some sort of a message. I need to take a look at it. All right, so Let me see. What I wanted to do next, I really want to actually set, you know, transform from a screen coordinates to the normalized device coordinates, because it will also fix the sizes of these particles too, the ratios between them. So it's gonna just look a little bit better generally. It's just generally gonna look a little bit better. Okay, so how are we gonna pass this information? We're gonna pass them through a uniform. Vec2 resolution, right? It's going to be vec2 resolution like this, and we will need the program. So we're initializing the shaders. So here's the program, and then we're losing the program, but we need the program to actually get the uniforms. So let's actually make the program global. I mean, it's a small throwaway program. We can make everything global, right? We can make everything global, not a big deal. And GLUint resolution uniform, right? So it's going to be something like that. And I think we need to get the resolution uniform GL get uniform location. I think that's what it is. Get uniform location. All right. So this is going to be that. And after that, we're going to be doing it like this. So the name of the uniform is going to be resolution, right? Resolution, and it's actually GLInt. Uniforms are GLInt, not UInt. Resolution uniform, and there we go. Yeah, of course. So now, after we initialize everything, we can yeah, this one is done essentially. Thank you for reminding me. GL uniform to F resolution uniform, and what we need to set in here, we need to set screen width, screen width, and screen height. Okay, semicolon. Okay, everything compiles. So now we get the resolution in here, right? And we need to map our coordinates in screen coordinates to normalized device coordinates. So how can we do that? So let me create a special function, something like vec2, and what is it going to be called? Screen. Yeah, let's call screen to NDC, right? Screen to NDC. So it's going to accept some sort of a position in here, right? So it's going to be some sort of a position, and yeah. 1, 2, 3, 4. 1, 2, 3, 4. So, okay, let's take a look at this kind of stuff. Let's take a look. So we have a value from -1 to, actually not from -1. We're going to have a value from half of the width to half of the, yeah, minus half of the width to plus half of the width. It's not to say it has to be width, it could be also height, but it doesn't matter. It's like symmetrical. You need to transform this to -1, 1, right? You need to transform it to -1, 1. Okay, so one of the ways to do that, right? So you have your x, right? And you know that x is basically this range, right? It's in this range. One of the things you can do, you can probably divide it by width, right? You divide x by width, and this way you have -half and +half. And then you multiply this thing by 2, and that way you have -1 and 1. So that's how we do that. The same applies to y. It's just instead of a w, you're going to use h. So that's the way you can map from the screen coordinates to the normalized device coordinates. Yeah. All right, so let's return something here. So return vec2 position x. You multiplied, you divided by width, and width in our case is a resolution x, and you multiply it by 2. To be fair, right, if you take a look at what I'm trying to do in here, all of that could be expressed in terms of the vector arithmetics. So essentially you can do pose divided by resolution multiplied by 2. So that's essentially what we can do in here. Yeah, good. That's pretty much it. That's pretty much it. All right. So, and then when we are constructing the vertices in here, we want to set some values in the screen coordinates. So now we can set something like minus 100, 100, then 0, 0, and 100, 100. That's going to be 100, 100. There we go. 100, 100. And that is not it. I think I forgot to do something. So it would be better to actually extract this entire thing and construct like a proper position, if you know what I mean. So let me see, maybe something like vec2 particle position. So we have a particle position. Okay, and then we want to split it like that. So this one is going to be something like maybe vector 2, right? So here's the vector 2. So position x is that, so we're generating some different things. What I'm thinking is that we don't need to multiply this stuff by half. I multiplied it by half because I wanted to actually reduce the size of it. But we don't have to do that. Okay, so here is this particle position, and we should stick that particle position in here, right? So it's going to be particle position, but it also has to be converted from screen coordinates to NDC coordinates, like so. And this is a new line. Okay, so I hope I didn't introduce too many compilation errors, so should be all right. A lot of these things could be also described in terms of a vector arithmetics. So maybe that's precisely what I want to do in here. So maybe I'm going to have something like UV coordinates. Who needs UV coordinates when you can have UV coordinates? Am I right? Am I right, fellow weaves? 1, 2, 3, 4. So, and we can put these things in here, I suppose. So this is going to be UV. And this one's going to be something like this. So now we have UV coordinates. Cool. So here are UV coordinates, and the UV coordinates, from UV coordinates you can get the particle position. It's actually not really a particle position, it's this thing is a particle position, but that thing is the mesh position or something. So in any case, what you have to do, you have to take UV multiplied by 2, right? But also subtract vec2 1, 1, right? And that way you'll get the right thing, hopefully. So after that, you can take this entire thing, right? You can take this entire thing, at the current position, and you've got yourself basically the mesh position that you can stick into converter between screen coordinates and NDC, right? And maybe this way you can remove that stuff. Okay, so you have UV coordinates, then you convert UV coordinates to the normalized device coordinates, you update the position, and yeah, you will see some particles, but they should be super small, right? So they should be around like 2 pixels small, if I understand everything correctly, and if this entire thing compiles, because it might not compile because I probably like made a lot of syntactical errors, but I don't see anything super obvious, right? I don't see anything super obvious, and well, that's in, well, wait, I think we saw, yes, you can actually see them. They're around 2 pixels. Yeah, here they are. Yeah. Okay, cool. That's actually pretty poog, not gonna lie. So we managed to render to like 3 particles. 2 hours in, 300 lines later, and we're able to render particles with OpenGL. Hell yeah, bro. OpenGL. So, is this stream even about fluid simulation? I don't know. Probably not. Probably not, but we can just, you know, render some particles now. So we can also probably customize the particle size. It's one of the things we can do. So did you know that you can actually use preprocessor inside of GLSL? Right. So I can do something like a particle size, and by default it's going to be like 1, right? And what I can do in here, I suppose, I can take this thing and multiply it by the particle size. Right, so here's particle size. And I can increase it by 2, so it's not going to be a little bit bigger now. So what about 10 pixels, 10 by 10, I suppose. It's actually 20 by 20, it should be 20 by 20 because the default size is actually 2 by 2. But yeah, now we can customize this size, and maybe around like 8 should be all right. And yeah, we have a system where you can just push a bunch of like particles in x, y coordinates, specifying their colors, and it will draw them really, really fast, right? And the maximum amount of vertices you can have is like 1024, right? You can have 1024. But yeah, so all that uses hardware acceleration, and maybe we'll be able to actually render them super fast. But so, as in, if you used Unity, it will be way faster. Yes, thank you very much. So maybe we should make a small break before we actually go into trying to simulate something, right? So one of the main things I see in here is that you need to have like these 2 structures. So you need to have a structure particle, which is essentially like it has a position, it has a velocity, and it has a mass, right? And you also have cells, and cell has a velocity and a mass, but it doesn't have a position. That's what makes it really interesting. It's like, what's the difference between particle and cell? And it's just like the program is actually like both. So we have a grid, and you have a particle. So but there's a lot of explanations in here, and if some of the explanations are not like clear, we can do something about them. I guess we can do something about them. I suppose we'll need some very simple like vector graphics library, just like something for to compute vectors, like add x and y and multiply and scale and stuff like that. So maybe I can quickly implement that. But in any case, I'm gonna make a cup of tea. So I'm already streaming for 2 hours, and I'm gonna spend another hour actually working on the fluid simulation. So yeah, I guess I'm definitely gonna put the maybe some sort of a timestamp to skip to this moment. By the way, I think I can actually do it right now. So description, timestamps. So the current timestamp is 204 like 30, around 30 or something. So then I can manually go there and just, you know, adjust it accordingly. But the idea of that timestamp is that finished OpenGL setup. Yes, finished my OpenGL setup. Isn't that cool? I think it's pretty cool. All right. So let me make a cup of tea. I could have just split this entire stream maybe 2 parts. So the first part is preparing for particle simulation, fluid particle simulation or something like that, and then another stream for actually simulating things. But I think I have another hour, so it's fine. It's fine. Okay, I'm gonna go to the kitchen, turn on the kettle to warm up some water for my tea, and I'm going back. Don't go anywhere. I'm not editing this video, so I'm sorry. So you just have to wait. Pretend that it's like it's edited. Just sleep for a couple of seconds. I don't know. So let's define these two structures, I suppose. Yeah, no. Let's go to like something like vec. Where I'm gonna put? I always struggle to come up with a name for like math libraries and whatnot. So because it's let's call. Oh, I know how to call this. LA.H. Yes, it's a linear algebra. Linear algebra. So LA.H. It's definitely not Los Angeles, of course. It's linear algebra. So, and in here, we're gonna have a couple of structures, right? So it's gonna be vec to f, float x and y. Right, float x and y. And we need a way to construct this entire thing. So it's gonna be vec to f, float x, and then float y, right? Do I have to say that it's a vec to f, because I'm not going to be using f like extra characters, so let's actually call it vec 2. It's going to be vec 2. So, and the other things what we need is vec to add, vec to a, vec to ab, then subtract. I definitely didn't finish setting up everything at that particular timestamp. I will probably have to make another timestamp. Man, my tea is ready. Just a second. So we need to do a scale as well. So it's where when you accept the vector, but you also accept the scalar. So you also want to be able to multiply them. So vec to mul. Multiplication is going to be component-wise. It's not going to be a dot product. And also division, just in case. So add, sub, multiply, divide. Scale. And that's about it, actually. Do we need anything else? I don't think we need anything else. We also need some matrices, so... Oh, yeah, so in that example, the matrices were not used, so maybe we don't need them. Okay, so let's quickly implement this kind of stuff. It's not that difficult. la.c include la.h, right? Pretty straightforward. We're going to use a lot of Emacs magic to facilitate the development. I'm going to quickly replace this thing with just one more time. One more time. GMCA incoming. this one, and look. Can your Vim do that? Aha! Destroyed with facts and logic. Is that meme dead? I think that meme is dead already, so... okay, so what do we have in here? We need to do something like vec2, ax plus bx, then ay plus by, and that's it. So now you can easily copy paste that and just replace the corresponding operations. So this is going to be subtraction, this is going to be multiplication, and this is going to be the division. Right, so this is going to be the division, and this one is going to be essentially, to be fair, you know how you can implement it? You can implement it as multiplication of a with vec2 s and s. There we go. Yeah! So we implemented all the necessary operations. Why people use separate programs for linear algebra? It's easy. Look. look, it's easy. Why do you need JLM? Come on. Alright, anyway, I'm joking, of course. So, maybe I could use actually vec2 now in a vertex definition. That would be interesting. In the vertex definition. So okay, so we have this thing, and now we have two translation units. So we're gonna do something like this. We're gonna link them together, and now this thing also depends on this thing, and also on this thing. So everything depends on this thing. All right, everything seems to be compiling now. All right, and I haven't committed anything. I don't even have a you know, committee pushy thing. So let's create a readme. So we're gonna put in there, I don't know, an attempt to implement okay, npm, an attempt to implement something that resembles the material point method. An attempt of dumb software developer to implement something that resembles the material point method. Because I am dumb, like I know nothing but, you know, I don't know anything. Okay, and npm. So we're also going to have dependencies, and the dependencies are glw, right, and glue, glw. All right. So here's the first dependency. Boom, glue. Random singing Pepper Pains. And we're also gonna have references. So here's the references. Main reference in here is this thing, right? So that's what we're using for the reference. There we go. License is gonna be proprietary license. Alright, so also maybe I'm gonna put git ignore in here and git ignore in this thing, and yeah, we can just do git init, and then we can do pushy, and not really pushy. I think I'm not gonna push it before I finish the stream, just to not spoil people who actually follow me and stuff like that. So let's do it like this. Ready, set, a go. Ready, set, a go. Okay, go. So the first thing, as prescribed by the guide, is going to be defining the structure for the particles and the cells. I still don't quite understand the point of the cells, but I'm gonna just trust the process, right? So this is a particle, right? So here's a particle. And we're gonna have something like vec2x, which is the position, right? So this is the position, and v, which is the velocity. So we're also gonna have a mass. All right. So we're also gonna have mass. And a cell is basically a particle without the position. It only knows its mass and velocity. So maybe we should read that. Okay, simulation structure. To set the scene a little, here is an overview of the structure of our data. We need particles and a grid. Here is the minimum required for basic MLS MPM simulation. Okay, so I know what is MPM. It's a material point method. What is MLS? Material something. Okay. Our particle mass will stay constant throughout the simulation. Okay, that's good. It becomes more relevant if you're doing multi-phase simulations, but in all my examples, it will just be set to 1. Oh, yeah, I think I know. I didn't know what is a phase. The fuck? I thought I wasted my time when I was in university, but I remember from university what is a phase. Holy shit, okay. Maybe university wasn't a waste of time. Our particle mass will stay constant. So, okay, already read that. Multi-phase, and here's our grid is made up of individual cells. It's literally just a big array of them. Okay. In the implementation below, I use a 1D grid for efficient reasons, but and remap to 2D indices when required. I mean, yeah, it's a classical thing. You can easily do this with a 2D, 3D array of cells instead if you like. The size of our grid determines the resolution of our simulation. Okay, if we choose a grid size of say 32 by 32, then our particle coordinates will range from 0 to 31 by 31. Okay, all right. It's common to use a power of 2 for the grid size for performance reasons when parallelizing. Oh yeah, because if it's a power of 2, it's super easy to subdivide the grid by 2 horizontally and vertically, sort of indefinitely, right? So we can indefinitely subdivide it by 2 and basically parallelize quite easily. If I understand correctly, I know nothing about parallel programming or anything like that. So for performance parallel, I'm usually using a grid size of 64 in the GIFs on the page. Okay, so maybe that's precisely what we're gonna use. Conceptual clear lapse. The grid in MPM is cleared at the start of every frame. It's just a scratch pad for calculating certain quantities. Interesting. And you chunk it away at the end, and you chuck it away at the end of each simulation step. So none of the values in the cell struct are constant throughout the simulation. I see. Oh, I see. It's like an intermediate computation thing. All right. So the main state of the simulation is in particles, but for intermediate things, you use cells. Okay. All right. Note, the above is the near minimum for getting classical MPM simulation moving. If we want more sophisticated behavior, we'll likely need to keep track of deformation gradient metrics at each particle. I don't think we're gonna do that, but okay. And some notion of their volume. When we move on to using MLS MPM, we'll add a little bit more info still. Namely, each particle needs to store an affine momentum matrix we talked about above for APIC. I don't know what all that means, and I didn't read anything above. I just want pretty pictures. In traditional MPM, you would also store a force vector at each cell. With MLS MPM, you can get rid of explicitly it and you can get rid of explicitly it entirely. Okay, maybe it's a typo. I think it's a typo. And instead fuse it together with the velocity update. Or maybe I'm reading it correctly. You can get rid of x. Okay. Simulation loop is outlined below. Okay, so let's actually just define these particle things. We already have a particle. And let's define struct. So this is going to be a cell. And we just have the velocity and the mass, right? So the mass and the velocity. Simulation below is below. Comrade. Below is an outline of the MLS MPM algorithm. At each step, I have included a brief note on what the algorithm is trying to do with inline reference to our FAIF papers. I don't know what is a FAIF paper. Maybe I should read that. I find it helpful to look at the broad strokes of how NPM actually runs around the data before diving into the specifics of how each step specifically transforms it. Hopefully it will clear up what happens where. For a more detailed step-by-step walkthrough, I recommend looking at the chapter 10 NPM schemeful algorithm. But we have the source code. Can't we just use the source code to do that? Maybe. All right. So here we have a bunch of particles. So how many particles do we need? Initialize your grid. Fill your grid array with grid res cells. All right, so let's define a grid. So this is going to be a grid, and we're going to have a grid res. We don't need to actually have a one-dimensional array and map 2D coordinates to one dimensions in C, because if you define a two-dimensional array in C, it actually stays linear in the memory. And you don't need a separate language that is called high-performance C# to actually make your program faster. I'm not even sure if it's a separate language. I know nothing about C#. Please don't cancel me on Twitter, okay? So let's define this thing. Okay. So they're using the resolution 32. Okay. They're using resolution 32. And how many particles are we gonna have in there? I don't know. Create a bunch of particles, set their position somewhere in your simulation domain. Initialize their deformation gradients to the identity matrix as they're in their undeformed state. Okay, do I really want to do all of that? Maybe. Okay, so how many particles are we going to have? That's a good question. So it's going to be particles, right? So it's going to be particles capacity, maybe particles count, because we're going to use all of them, I suppose. We're going to use all of them. And let's define particles count equal to, let's define like 100 of them. And another interesting thing I want to do, actually, I want to statically assert that particle count is less or equal to the verts count, right? So we don't want to basically have more particles that we can physically render, right? So if you have more particles, you better just increase the amount of vertices they can render. Or maybe we can actually make them the same thing, I don't know. So it could be something like actually verts count. Why not? The amount of particles you have is the amount of vertices you can render in the first place. Sounds good. Sounds good to me. Maybe that's precisely what we want. Okay, so so when we're initializing everything, I think like I don't really know what to fill it with. That's the problem. Like, what are we filling it with? Example: getting things moving. Source code. And it's just, it doesn't point at the specific source code, it just points at I'm using a neat trick for calculating the weights that I first came across. The Youngmin, who, I hope I pronounced their name correctly, I'm really sorry if I didn't. 88 line MLS MP. Oh shit, maybe we're gonna use this thing? Wait. Incremental NPM. Wait. It's just a bunch of references. Where is the... Oh, here it is. Maybe we can use that. Maybe we can use that. That would be actually kind of cool, I think. So this is 88 lines. And that's a lot of stuff. It's, I think... and there's also a lot of like comments in here, but the actual amount is actually pretty small. Nah, it's too complicated. Okay, so let's take a look at the keep forgetting where this is. Packages. It's not packages, it's assets. It's really quite confusing for me because the actual code is located in assets. Like, okay. All right, here is the code. Right, so we don't really need this thing for this file. So I suppose this is the intro. This is the intro for this is this thing, probably. I don't know if it's actually intro or something. We also have a padding, but I'm not sure if we need that padding. Maybe we do. That would be interesting. So we have x, v. Oh yeah, since we don't have the matrix, probably we don't even need to pad it. But you still have like 5. Maybe it would make sense to actually add padding because you have 2 floats, another 2 floats, and then 1 float. Let's actually pad it to like 2 floats as well. All right, so a cell, also just a padding. Maybe we can also add padding in here. I don't know what I'm doing. So we have a grid resolution, which is 64, right? In this example, it's 64. They're mapping things. Time step of our simulation. The stability of our simulation is going to be limited by how much a particle can move in a single time step. It is a good rule of thumb to choose it dt so that no particle could move more than 1 grid cell in a single step. This would lead to particle tunneling or other very unstable behavior. Okay. Also, by the way, since I'm primarily going to be working with this file, I'm going to put this file into the description as well. Right, I'm going to put it into the description as well. So, so the iterations. Not really sure what they mean by iterations. So, oh, I see. Iterations in a single second, right? So if it just depends, what do we mean by dt? dt probably is in seconds. So we also have a gravity, amount of particles. Here are the particles, native array. Yeah, I see. It kind of reminds me of JavaScript's JavaScript uint8 array. Yeah, it kind of reminds me of that. It's just like these managed languages, they need special bridge between them and the native stuff. So we also have weights, whatever that's supposed to mean, simulation renderer, whatever that's supposed to mean. So interaction, I'm not sure if we care about interaction right now. So initialize a bunch of points in a square. So start. So we have a temporary position, right? So list of temporary position. So what we're doing here, and we have temporary positions, and we have an amount of particles, and then we're just okay. So we're essentially generating generating a bunch of positions, and we use those positions for the particles, right? And then we are initializing the grid, and the grid we just initialized with empty empty cells. We're not doing anything particularly special. Okay, seems good to me. Real voice, by the way. So when we update, we just go through the iterations and we simulate, and we render a single frame. Okay. During the simulation, I guess in our case, rendering is going to be iterating through all of the particles and pushing them into the vertices. So that's pretty much going to be the thing. A simulation. Okay. So we iterate through the cells, we set their vertices and mass, and then we do P to G, whatever that's supposed to mean. I don't know what is a P to G. Maybe we can actually learn that. So quadratic interpolation weights, blah, blah, blah. Grid velocity update, and G to P. Oh, I think it's some sort of a conversion. So we're converting. Oh, it's a particle to grid. Okay. I see. As the paper said, the grid is some sort of like a scratch pad or whatnot. So it's needed for intermediate calculation. So you have the current state of particles, and you convert them to grids, right? and then you do some sort of a like grid velocity update, grid calculations, and you need to convert grid state back to vertices, and at that point you can throw away the grid. I guess that's roughly how it works, right? So that's why there's a like a particles to grid and grids to particles. Interesting. I'm not a physicist. I never did any like fluid simulations or anything like that, but I roughly understand what the fuck is going on here. Like on a, like out if you or like on a bigger picture, right? So I roughly understand this entire source code, and I think I could be should be able to translate it to C and just see if it works or not. Okay. I'm sorry. Okay. So how are we gonna call all of that? So we're gonna do something like npm start. So this is how I want to call it. Right? It's gonna be just npm start, just npm start. What we're doing in here is that we take the grid size divided by 2, box x and box y. So yeah, we're actually, it's important to keep in mind that we're implementing a very like not ideal version. It's single threaded. It's just like a small intro, but that's precisely what I want to do. I don't want to overwhelm myself with like a lot of things. So we have a spacing of equal to 1. So this is basically what we have. So here is a spacing. Then we have a box x and box y. So we have a bunch of boxes. And then we take a grid resolution and divide it by 2. Maybe we do that for like the quadrants or whatnot. I think that's what we do it for. We do it for the quadrants. Okay, let me just copy paste this chunk of code. Right, so it's going to be that. And then we start iterating. So we're iterating from Sx. Yeah, I think that's what we're doing. We're doing that for the quadrants. And then we do spacing. And that gives us a bunch of positions, right? And this is where we accumulate these positions, I suppose. This is where we accumulate them. So essentially the amount of particles that we're gonna have depends on the grid resolution, and this is precisely where we're generating them. Right, I think. So I'm gonna just temporarily remove that, and I wanna take a look at what do we even have in here. So it's gonna be something like vec2, f, n, I, j, there we go. And let's see how many of them we're gonna have. So maybe I'm gonna have something like size t count, which is gonna be count plus 1. And let's print something. We got ZU particles. Right, we've got ZU particles. And okay, so we don't have vector 2. This is because we never included Los Angeles translation unit. Okay, and what do we have here? So it's a verts count. Is it not? I think it's verts capacity. Yeah, it is verts capacity. And what else do we got? It's a grid res, because it's a big one. Okay, so what do we got? We never actually called the start, and also we have this thing. Yeah, we got particles, we got count particles. All right. So let's call this function before doing any simulation, right? So we essentially prepared everything, right? And it's just npm start. So we start in the simulation. What do we get? So we got 256 particles. Okay, that's very interesting. That is in fact very interesting, and their positions are like around like 24 or something. And since we don't really know the amount of particles up front, maybe but I mean we can know the amount of particles up front. We can calculate their this amount at compile time, if you know what I mean. But it involves like a floating point computation. but maybe it's like easier to just follow this example, and maybe we're gonna optimize it a little bit better next time. So the problem with this example is that it computes the amount of particles in the simulation at runtime, when in reality it could have been computed at compile time, right? It's like, oh, it's based on all of the values that are known at compile time. So but maybe it's not that important, right? Maybe it's not important, because at the end of the day, a physicist just wants to get the job done, right? They care about the end result. They care of the ways they get it, right? It's a runtime, compile time, who cares, right? So, but I'm being stubborn C developer. I want to do that at compile time, because I think it's cool. And that's why I don't have a PhD in physics. Okay. So let's just follow their logic, I suppose. So amount of particles is going to be maybe Wert's capacity, and I don't know, maybe we're going to have some sort of particles count. Particles count, right? It's going to be particles count. So particles count, and how much capacity do I want? And what's interesting is that so this is a temporary solutions. Then we iterate through the entire thing, and we just use the temporary solution, right? To be fair, like, what's the point of actually doing it like that? Like, what's the point of separating these two arrays? Because you could have just moved this body inside of in here, and you wouldn't even need a temporary positions array unless you use temporary positions for something else. But this is a really strange way. Like, why do you need temporary positions here? Excuse me. You can just generate them directly, and you don't need to allocate anything. Okay, so that's it is what it is, and it isn't what it isn't. Okay, so there's particles count. Yeah, and the actual position in here, right? So the so vec2 position is going to be vec2 ij, right? And let me remove all of that, right? So, and when we are creating a new particle, right? So this is going to be a particle, and we set that particle in there, right? It's going to be particles count, and its x is going to be actually vec2, right? It's going to be vec2, and then the velocity is going to be absolutely random. Okay, this is actually kind of cool. The velocity is supposed to be random, but what's the range of this kind of stuff? What's the range of it? So I need to close some of these tabs, because they kind of distract me from what I'm doing. Okay. So random value, C#. Why do programmers wear glasses? Because they got C#. I'm funny. Okay, random value. Really? What's the range of this thing? Random value. Is it a Unity thing, or is that a C# thing? This doesn't explain it. Do they import something? Random Unity engine. Okay, it's a Unity thing. Okay. Unity random value. Okay. Unity people. Okay. Random value returns a random float from 0 to 1. Okay. So we need to also have something like that in C, right? So essentially we could use crand, right? We could use crand, but the rand returns you a value from 0 to max. the rand returns you a value from 0 to rand max. So let's introduce a small little function. Let's introduce a small little function called something like, where am I going to put that? Rand float, right? Rand float. And essentially what we're going to do in here, we're going to take the rand, convert it to float, right? And then divide it by rand max, or yeah, rand max, also converted to float, right? Also converted to float. And we're going to return the float. So this entire thing is going to return us values from 0 to 1. So let me even demonstrate you. So we can comment out this thing. Let's create another entry point, right? So I can iterate from 0 to 10, right? So it's going to be plus plus. It's going to be print f. It's going to be f. So rand float. Here we go. So we have a rand float. And this one does not exist. We don't need this code anymore. And there we go. So now we have a function that returns a value from 0 to 1. Isn't that amazing? I think it's goddamn amazing. So if you always wanted to have this kind of function in C that returns a value from 0 to 1 rather than this rand that only returns integers, you can do it like that, right? Because it returns a value from 0 to rand max. So that means the result of rand is always going to be smaller or maybe equal. Yeah, smaller or equal to that. And if you divide smaller value by a bigger one, you always get a value less than 1, right? You always get a value less than 1. So that's how you can achieve the same thing, right? It's pretty straightforward, pretty simple. Pretty simple trick. Right. You don't need a Unity engine to generate a random value from 0 to 1. You don't need a whole goddamn engine. So we have a positions and we need to generate a random velocity, right? So it's going to be particles count, that. All right, so in math, this one is vector2, this one is rand float, this also is rand float, and I guess that's it, right? So this is basically what we have in here. Yep. So we don't need transformation, we don't need math. Well, we do need math, but it's going to be constant anyway. Particles count, and it's going to be something like mass 10. And after that, we just increment this entire thing by 1, right? We just increment this entire thing by 1. All right. I guess that's it. Believe it or not, like, I don't quite understand what the hell is going on in here, but you can compress both of these loops into a single one. Yeah, this thing just does whatever this thing does. Like, I don't quite understand why you need so much code. But again, we don't even know if it works or not yet, so we're about to find out. And another interesting thing is that we need to assert the capacity, right? So particle count should be less than vert's capacity, otherwise you won't be able to do that, right? I kind of want to do the following thing, particle capacity, and I just make it equal to vert's capacity. So I can have like particles capacity, and here we're gonna have a particles capacity. All right. Anyways, so we initialize this entire thing. Now we need to initialize the grid. So in terms of a grid, we're just going through all of these things and setting them to 0, I suppose, I presume. We don't need to do that, because just by declaring it like that, it's already initialized, right? So that's the whole initialization, if I understand correctly. I think that's the whole initialization. You also need to like initialize the engine and stuff like that. That's understandable. So that's totally fine. Iterations. So the simulate is the most interesting part, I think. I think simulate is the most interesting part. Okay, so I can see that this entire thing compiles. And so we also don't have a cert for some reason. Wait a second, do we even have a cert for a vert function? We need to have a cert for a vert function because it's quite important. What if you overflow the vert's capacity? Right, it's quite important to have it here. Okay, so we'll also multiply this entire stuff. Oh shit, yeah. So we have to do vec2 scale because we're programming in pure C where we cannot overload the operands. So that's what we have to do in here. But apart from that, I think it's working. I think it's working. Okay, so let's implement simulate. So we iterate through grid. It's a really strange way of doing that. Like, why do you do that? It's even more readable, like, and furthermore, don't you have like a for each in C? Okay, I'm sorry, it's bike shading. It's bike shading. Doesn't matter. Okay, so let me see. So let's have a simulate. Right, let's have a simulate and simulate. That's what we're gonna have in here. So I guess we need to have something like reset grid scratchpad. Then we have to do points to grid, right? Points to grid. Then grid velocity update. We need to do grid velocity update. That's quite important. And then we'll have to convert everything back to what it was. Right, everything back to what it was. And yeah, I guess that's it. So that's pretty much the whole example, if I understand everything correctly. All right, so let's reset grid scratchpad. Right, grid scratchpad. In our case, I think I'm going to be just doing something like for size ti less than grid resolution plus I for size tj grid resolution plus j, and then we're going to just set grid ij, and we're setting the mass to 0, right? We're setting the mass to 0 and the velocity to 0 as well. We're zeroing everything out, So now we need to iterate through num particles. So a single particle u int 2. Oh, okay. U int 2. So let me actually see if this entire thing compiles. Yeah, it has to vec2. So I have a feeling that we'll have to have two separate versions of the vectors, unfortunately. We'll have to have two separate versions of the vectors. P to G, Gx and Gy. So then we take the weights. We also initialize the weights. And weights is something that is allocated in here, and it's basically an array of 3 elements, right? And I'm not quite sure. Okay. So it's literally an array of 3 vertices, which is used quite rarely. Like it's used first in P2G, as far as I can tell, right? So it's first in P2G, then it's used in G2P, right? And it's only used within the simulate, if I understand correctly, right? It's only used within the simulate. So why is it not allocated inside of a simulate on the stack or something like that? Maybe because of C#. maybe because of the C#, like in C#, like allocating on the stack and deallocating maybe takes too much time or something, but we can easily do that in C, right? We can just allocate that in the stack. So let's quickly do that. So we're gonna put it in here. In our case, it's gonna be vec2, and it's gonna be an array of like these three things, and it's initially gonna be filled with 0. Simple as that. Is as simple as that. So now we are starting to iterate. I'm gonna actually put it in here. So for 0 less than particles count, right? Because num particles is the particles count in our case. Then here is the particle itself, right? Here is the particle itself. So maybe I'm gonna actually keep it as a pointer. So it's gonna be particle p. Do we really need to copy it? Because it doesn't. We don't really set it anywhere. Right, we don't really set it anywhere, so it doesn't really matter. So we can just save it in here. So it's a particles, particles I. There we go. So this is a particles I, and then we need cell index. All right, it's a cell index. In a cell index, we take the position of the of the particle, which is a float position, right? And we basically truncating it down to unsigned integer. That's essentially what we're doing, if I understand correctly. And really, so you truncating it to the thing, right? Then you take the original position and you subtract it, and then there's a cell difference. Okay, but why are you truncating it though? Why not floor, for instance? I guess it doesn't matter because everything is in the positive coordinates. That's probably why. Right, so like it doesn't matter whether you want to floor it or truncate it, because to get the bugs, because of the truncation instead of float, you will have to work in negative coordinates, and this thing doesn't work in negative coordinates. Okay. I guess it's kind of weird, but okay. So we also have a difference, and we use that difference to actually calculate the some sort of like a weights, right? Quadratic interpolation weights. That's what it is. It's a quadratic interpolation weights. So for all surrounding cells, then we do something. All right, okay, let's actually try to do that. So I'm gonna take this thing, and in our case, I think it's gonna be something like unsigned int cell ID x, cell index, and it's gonna be x, right? So that means I'm gonna be doing something like unsigned int px x in that particular case, right? And this is gonna be y. It's gonna be y. I could have created like a separate type for vectors and whatnot, but I couldn't be bothered to do that. So instead, a single variable, we're gonna have two variables in here. So then we're gonna have a cell difference, right? So this is gonna be a cell difference. In that case, I basically take the original thing, right? I take the original thing. Might as well actually take px, but then I will have to construct something like cell idx x, cell idx y, and convert it back to floats, right? I'm converting it back to floats, and then I'm subtracting them. So it's going to be vec2 sub, right? It's going to be vec2 sub, and then when I'm trying to subtract, you can subtract scalars. Okay. You can subtract scalars. So I suppose the vector implementation here is overloaded, and let me take a look at the Unity mathematics. I never worked with Unity, so yeah, I didn't even know. Unity mathematics is there. Okay. Let me go back. Overloaded operators. Will we find anything here? Struct float 3. Let's take a look. That's what I want to see. Okay. Operators, okay. So, returns the result of component-wise addition operation on float value and a float 3 vector. Okay. So essentially it takes it can take a single scalar and add it to each individual component of the vector. All right, that makes sense. Okay, so it automatically just constructs it out of it. I suppose it would be kind of cool to take a look at the implementation of this thing. It would be cool to have like a source code. But yeah, returns the result of component-wise. All right, makes sense. Makes sense. Again, I'm not a Unity developer. I know nothing about Unity, so forgive me. Okay, so it's gonna be so we're subtracting that, and we need to subtract this thing yet again, but we're gonna be subtracting a vector 2 0 5 f 0 5 f, and it's gonna be like that. Okay, so yeah, so px subtracting this entire thing, and then we're subtracting again this entire thing, and that's going to be our cell div, right? This is our cell div. Okay, so let me see particles count. This one has to be size t. So this is unknown type float because it has to be vector. And everything seems to be working. So it just complains about these things being unused. So now we're iterating through the cells. So we have gx and gy. All right. So let's take that. Gx and gy. So the weights is actually 3 weights. Maybe that's why we do it like that. So oh yeah, I forgot to actually calculate the weights. Yeah, that's true. I completely forgot about that. So we the power. So oh, this one is interesting actually. All right, cell div is a vector. So that means in here, what we have to do is just take a vector 2 and just do it like that. All right, and when you rise, and this one of course is a sub vector sub, you're subtracting this thing from another one, right? So it's going to be like that, and you rise it to the power of 2. So it uses math power. Okay, Unity math poll. Let me see. But maybe it's kind of math. Yeah, so it's from the same module actually, right? Because float 2 and stuff like that, they are also from math, right? Because there's math float 2. So that means we need to find this thing, Unity math module, module math. I just want to find the, okay, but it's math. It's not what I need, it's math. How can I find the math module? So can I just do float 2 and just find what I want? Can I find float 2? Let's make a cup of tea, shall we? I'm already doing that for 3 hours. I'm already 3 hours in. And to be fair, the only work that is left in here is to just go through that example and translate it to C, which is not that bad, but I'm a little bit tired. So let me think. I think I'm gonna go for another hour. So it's going to be maybe 4-hour stream. And so hopefully by the end of the next hour, we will have this thing translated to C, and maybe we'll see some movement. So the problems that I expect here are probably with the coordinate system. So this entire thing uses one coordinate system, but we are assuming a completely different one. So it feels like they're trying to do everything on the positive quadrant, right? So, but we are actually at the center, right? So we have like quadrants at the right, left, and down. So 0 is the center in our case. That's what I'm trying to say. But we can also shift all of that. We can always shift all of that in shaders somewhere. So because it's just a matter of how we map the coordinate system. So we just have to be aware of all this stuff. So yeah. Okay, so I guess I'm gonna make another break. It's almost like I'm doing a Unity stream. I never worked with Unity, but so far it looks pretty straightforward. It's just, yeah, I guess. You just have a vectors, and you can then just ask the engine to render things. That's what it is. That's what it is. That's what it feels like. Okay, so let's make a small break. So it's gonna be 3 minutes. I'm gonna go pee and also warm up some water for my tea. And maybe you guys want to listen to some music. How about that? How about that? All right. Some people are writing me in Discord. Hello everybody, Zodi, thanks for the offline stream. You're welcome, MatesF777. Thank you for watching them. I really appreciate you watching them. Okay, let's listen to some music. All right. Right. Have fun. Hey yo, what's up? How's everyone doing? So I would assume that math_pow performs component-wise rising to the power of certain value, right? But I just don't want to assume that, right? I want a confirmation from the documentation. Confirmation from the documentation. Yo. Sorry. Paper pains. So Unity power vector. Maybe we can do something like float 3, maybe some of them. Float pow. It also feels like there's kind of discrepancy. So there's a math f, but at the same time, maybe this is an old Unity of some sort. I want to be 100% sure that I'm doing the right thing. If I try to just find float 3, Unity struct float 3. Right, this is what I wanted to find. Here's a float 3, and it's Unity. It's Unity Mathematics. Okay, that's why I couldn't find it, because it's like okay, it's called Unity Mathematics. So if I have some, so this is a data structures, right? Do we have a pow on there? Okay, so here's that. So there are classes. Here's the math class, and in the math class we should have something like a pow, and it's a huge. Oh my god, this is a huge page. Okay. Oh my god. Well, I mean, I also have a. All right, this is what I'm talking. Okay. So return the component-wise result of rising x to the power of y. Component-wise, yes. Easy. All right. So basically, you have different combinations of types and stuff like that, right? And it's a component-wise rising to the power. All right, that's cool. So in that particular case, if I'm looking at something like that, right? What I'm doing, I'm actually rising these two things like to a particular power. Maybe. So do we have like a math pow anywhere else? Right, so in all the places where we rise things to the power, like especially vectors, the power itself is a scalar. So maybe I can have just a single function, somewhere in LA that rises things to a particular power. And I wonder if it has to be like integer. So this thing is an integer, so that means we can just like use binary rising to the power or whatnot. But maybe C has something like power. Okay, my tea is ready, by the way, so I need to go and warm up and pour myself a cup of water. That's what I wanted to do. That's what I wanted to do, mate. Okay, so all of that is actually like it's integers, so maybe we can implement our own thing. All right. So maybe we can do something like vec2 power, vec2 A, vec2 B. Right, and Okay. Oh. Let's see. It's a component wise. Just thinking, I want to have a constructor for the vector that takes a single thing in here and in fact returns you something like this. But I can't do that in C because there's no overloading or anything like that. So I have to call something differently. So what about vec2 s for scalar, right? vec2 s for scalar. I think that will be actually fine. Right, so it's gonna make it a little bit easier to do things. And maybe because of that we don't need scalar anymore, because every time you need to scale a particular vector, right? So you have something like scale, right? It's gonna be a and then value. You can always just use multiply, but wrap this thing into vec2 s. See what I'm talking about? It kind of makes this thing obsolete, yeah. So we just need. Yeah, we don't need that thing, so this is going to be the set of the things we need. And if you want to rise a particular vector, right, you have a vector a, and you want to rise it to a particular power, to the power of 5, you just do vec2 s 5, and it rises it component-wise. Okay, I think it's going to make it things a little bit simpler. All right, so we don't need scale anymore, and power is going to be simply vec2 ax pow f. So I think it's called pow f, right? C pow f. So it's base exponent and shit like that. Okay. Pow f a x b a y b y. Okay, I hope I didn't make any sort of mistakes in here, but we also need to include math in here. So here is math, and in here I also have to link with the math library. Math library, instantly demonetized, by the way, instantly. Talking about drugs. Okay, so I'm not even monetized, so it doesn't matter. I don't even know what I'm talking about. Okay, let me try to compile this entire thing to see if it compiles. So you don't need to scale anything, you can just multiply it like that and then do vec2 s like this. And unknown type. Okay, so this also needs to be commented out. And do we have anything else? Cell diff, unused variable, that's totally fine. What about this one? Semicolon. Yesu, kawaii, fokendesu. So let me actually do committee here. So introduce vec2 s. No. vec2 s and vec2 poll. That's what we're gonna have in here. vec2 s and vec2 poll. It's not salty enough. It's bland. My tea soup is not salty. All right. All right. So what we need to do in here is essentially vec2s, right? And then just vec2 sub, right? And there we go. We subtract these two things. And then if you want to raise it to the power, you have to do vec2 power, right? vec2 power. But this one has to be vec2s like this. And then if you want to multiply this entire stuff, you can do vec2s and just vec2 mul. Okay, look at that. And you probably want to get rid of this kind of stuff. So multiply that, Maybe I can do it like this. It feels almost like Lisp. Look at that. But yeah, that's pretty much the idea in here. Okay. And this one has to be probably F. Well, some of the things could be actually like compressed like this. Maybe we can store the original That's exactly what I want to say. Chat, do you store your original or you don't store? Okay, sorry. All right, so we're gonna have in here. Yet again, so this one is gonna be vec2 pow, cell diff, vec2 s, and then this is gonna be vec2 s, that, and just vec2 sub. Okay, my library actually makes it super easy to translate the Unity expressions like vector math expressions to my expressions. You just wrap things around in the same shape, and it's just like, yeah, that's how we do it. It's actually pretty cool. I really like that. So this one is going to be vec2 s this thing, then vec2 add. I need to get rid of that, and then it's going to be vector power, vec2s, and this one is going to be vec2s, vec2 power, and it's going to be something like that, and there we go. All right, so it's going to be that. Do we need anything else? Maybe not. But I forgot to store the original so let's put the original in here. Okay, cool. Nice. Nice code, by the way. Thank you, C. Very cool. Okay, it does work actually. Variable set but unused, and it compiled the first try. We'll look at that. It compiled first try. So now what we're going to do in here, we're going to be doing a two-dimensional iteration of our nation. So and then we take the width, right? We take the width, the weight, not width. Oh my god! And what are we doing here? So we take x and y. Oh, okay. Oh, okay, that makes sense. Yeah. All right, all right. So we do this cell thing yet again. Something yet again. So there's a cell. Maybe we need to introduce like unsigned int thingy, uint2 or whatnot. I feel like we need that because it will make the translation a little bit easier for us to understand. But yeah, I'm not 100% sure. Not 100% sure. Okay, so this one is what? Quadratic interpolation weights. All right, quadratic interpolation weights. That's what it is. Okay, maybe it makes sense to actually introduce something in here. H, so it's just a vec2. Maybe we can have ivec. the binding of ivec. Ivec2. You know what I mean? It's kind of similar to, like, I think it's also in GLSL. GLSL ivec2. Do you have an ivec? Yeah, it does have an ivec. Okay, so like a regular vec is a float, and this one is ivec. So maybe it's gonna be integer. I don't quite understand why you need unsigned in there, but I mean, we're gonna use integers, and if there any problem arises because of that, we can always fix that. No biggie, no biggie. Okay, so, and what we can do in here, by the way, we can just pretty much copy paste this entire stuff and just translate it like that. Right, and here what I have to do is just like I need to replace floats with integers, and here we're expecting I, and so yeah, you can just do that with a copy paste. So I can probably want to separate this kind of stuff like this, so I can easily find this entire stuff. I'm going to query replace vec2 with ivec2, right? Then just query replace vec2 underscore with ivec2 underscore, like this. You know what? I could have actually easily just do it like that, and I think it doesn't restore. Okay. Emacs is not very smart. What can I say? Emacs not very smart. Okay, so then I vec2, right, like that. So I'm not sure about power, so maybe I'm gonna just remove the power for now. So we're not gonna have a power for integers. But apart from that, I think that's pretty much it, except I didn't rename the floats to integers. Right, I didn't rename the floats to integers. Okay. Do we have anything else? Oh, okay. As I'm streaming already for 3.5 hours, okay? Don't get mad at me for making stupid mistakes, please, please. No. It's just like every time I'm getting tired and I'm starting to make stupid mistakes, people get really angry at me for doing that. Like, yeah, really? Mistakes? Really? So please, I also want to finish that. Trust me, I also want to finish that. Just give me some slack, okay? All right, so cut me some slack. That's the saying, I think. I back to okay. So, and we're kind of close, right? So we just need to port that simulation thingy, right? We just need to port that simulation thingy, and that's going to be it. And the reason why I wanted to do all of that is because, yeah, because that may simplify this kind of thing, I guess. We need to also have a way to convert this stuff, to convert one kind of vector to another one. So for instance, I want to be able to construct ivec2 from just vec2, right? I just want to be able to, but I'm not sure how to call that thing. From vec2, but it's too big, I think. It's kind of too big. Maybe to make all of that smaller, maybe we should rename vec to just v2 and iv2. I guess it's fine for now. I'll see. And we need to also do this kind of thing like the other way around. So it's going to be return ivec2 ax. This is going to be integer, ay and integer. There we go. So we have that, and also the other way around. We're going to have it like this. So vec2 from ivec2. And interestingly enough, can I just forward declare that thing somehow? Yeah, I think we should be able to. Right. So now we're interconnecting them. We're actually interconnecting them. LAC. It's going to be something like that, and we're going to return vec2 from ax, ay. We're going to convert them to float, of course. Converting them to float. It's quite important. Anything else? Cool. So let's go back to the original code. So in here, I want to set up ivec2 cell idx, right? So dx. And what I do is I vec2 from vec2, px, and that's pretty much it, right? And then we want to subtract that, but to subtract that I need to convert it back, so it's essentially vec2 from ivec2 cell idx, and then I subtract and everything should work correctly, hopefully. So now it's a little bit closer to the original thing, right? It's a little bit closer to the original thing. The original thing was like this, and that one just involves all of these computations and whatnot. Okay. It's a little bit closer to the original thing. Okay, it even compiles. Cool. So we're gonna use integers instead of few ints. It doesn't really matter that much. Then we're gonna do it like that. Cool. So let me take this thing. What's interesting is that this line like directly translates to here. So that's nice. It's always nice to have. It's always nice to have. Right, okay, so I might actually paste it, and we're gonna have a cell x, which is ivec2. So then I'm constructing ivec2 from x plus g minus 1, and I think that should work as well. So yeah, just constructing ivec. The binding of ivec. idx isn't declared, but it is declared. Wait. Did you mean? It's because of the scope. I wanted to be fancy and actually just have it like that, but then it's a stupid idea. Scope didn't leak enough. There was not enough scope leakage. Essentially, I put a scope around this thing to sort of emphasize the block, but because of that, the variable didn't leak into the scope anymore, so we didn't have enough scope leakage. That's basically what happened. So now we need to calculate the distance in here. Okay, so here is that. I'm going to comment it out. So we take a cell x and we subtract them. Interestingly enough, I think if you just try to do vec2 sub, it's not gonna work, right? Because cell x is ivec and you cannot just translate them like that. So we'll have to actually convert them explicitly. And this one vec2 s, right? And I guess that's what we're gonna have in here. And this one is just vec2. And yeah, of course. So we need to do vec2 from ivec. Like this. So we're adding these things together, and I'm gonna even put it like that, so it's a little bit more readable. But readability is a subjective thing anyway, so yeah, it is what it is. So Q. I think it says that it doesn't use the deformation matrix in this particular case, right? It's a momentum matrix, okay. So unused in this file. All right, that's very interesting. But it's still used in here because it's used for Q and stuff like that. And then it's used for the final velocity. Huh. For the final velocity. Scatter mass to the grid. So so then we multiply these two things together. Do we ever set? I think we set when we can, yeah, affine momentum. When we generate the cells, we set this thing to 0. So that means it's a 0 matrix. When you set, so I need to find. Okay, I actually instantly found it. Okay. Constructs matrix from a single int value by converting it to a float and assigning it to every component. Okay. So I presume something like that will be called if you assign it to 0, right? So that means it's a zero matrix, not an identity one. Right, it's a zero matrix and not an identity one. And because of that, I wonder if this entire example even works. Imagine like me spending a lot of time just trying to translate it, and then it doesn't work. But it's do they say anything in here at the top? So it is intra single threaded, right? So I suppose it's intra, like maybe this one. Is this intra? Just a second. Open image in new tab. Maybe it is, maybe it is not. I don't know. Hard to tell. Hard to tell. Okay. Forgot what I was doing. So if it's zero, right? If it is in fact zero, so multiplying all of that is going to give you just 0q, right? So then you can take the mass contribution. And then if you add these things together, you're probably, yeah, I think I'm going to just go ahead and ignore this kind of stuff. So you construct a Q, it's nothing, right? It's literally nothing. And then you use Q in here. And if it's nothing, that means it's not going to modify this entire thing whatsoever. That's going to be basically my assumption in here. So, which might be wrong, which might be completely wrong. Maybe it's completely fucking bullshit, but yeah, so it could be true. Anyways, so we have a cell distance. And okay, I can maybe put this thing here just for the documentation, right? And so ignored. This thing is ignored. Then we want to take this thing. Right, it's gonna be something like that. So and in here I take the weight and p mass, and it's just a regular float, right? So it's gonna compile. Yeah. It's quite rarely I can copy paste the line and it will just compile. It will just compile. So cell index. So we have cell XX. But I know that cell X in fact is IVEX, so we don't need to convert that. So then we take a grid size, and we don't even need to do that because it's already integer. All right, then we take the cell, we extract the cell, and everything is okay actually. So this entire thing can be just directly converted, which is kind of nice. And this one is actually a constant, a compile time constant. Okay, so grid invalid initial. This is basically translating two-dimensional coordinates to the one-dimensional one. We don't need that actually. So they use x as row. In fact, that's very interesting. So they use x as row because usually in here you put the row basically y. But they put x in there. It's like a classical maybe mistake. I'm not sure if it's a mistake in this particular case, but it's a classical mistake that people quite often make when they translate 2D coordinates to 1D coordinates. They confuse what is row and what is column, and it's actually quite understandable. So it's really easy to confuse. But I think in this particular case, it doesn't really matter much, because the dimensions are equal, so it's a square, right? So it doesn't matter if you confuse something, and maybe at the end of the day it's gonna just work. So we're gonna follow this entire thing like this. So it's gonna be cell XX, cell XY, right? In C it's quite easy to do that, and it's also quite fast because two-dimensional arrays in C in memory are stored like row-wise. They just like straighten up, and there we go. You don't have to worry about that too much even. It's very cool. So also we have a mass contribution, right? So we take the cell, we add the mass contribution. Is it gonna work? Is it gonna work now, yo? So then we take the cell and we add this thing in here. All right, and what's interesting about that thing is that I think we can straight up ignore this stuff. I'm pretty sure. So V is a vector, so that means we'll have to convert this thing back to S. And mass contribution actually. Oh no, the mass contribution have to be converted back to S, and this one has to be removed. This one has to be removed, and this is a vec multiplication, so it's going to be vec mul. vec_mul, and it has to be added. So it's got to vec2 add. Cool. Wait, what? Oh, it was my. I need to stop streaming. Oh, holy shit. Like, it was my mouse, and I, like, just see, like, there's 4 points now. I expected 3. Look, where's the 4 points? It's my mouse. Ah, this is the 4th hour. Holy shit. Okay. We're almost there. We're almost there, boys and girls. We're almost there. We just need to keep pushing. Keep pushing. And again, I don't quite understand why we copy this thing. Like, copy it, then put it there. It's just like, what's the point of it? You know what I'm talking? Like, cell XX and cell XY. Right, you extract this copy and you do that. Like, why do you do that? Like, seriously. Okay, I can probably make it work. So, and also we have a cell distance. And do we even use cell distance for anything? Wait, do you use cell distance? Oh, since we don't use cell distance for the Q matrix, we don't even need it. Okay, I can comment it out. All right, that makes sense, I suppose. I swear to God, if it's not gonna work afterwards, it's gonna be so sad. It's gonna be truly sad. But one of the things I wanted to say is that you can rewrite like this entire thing in a very, like, I think in a simpler manner, but I'm not sure if it makes sense in C#. Maybe in C# it's too slow. Well, you know, you're too slow. Too easy. Piece of cake. Okay. So, and in this one, it's gonna be like the... Well, I mean, for this kind of computations, okay, you convinced me, I'm an idiot. I'm tired. Yeah, it's a little bit easier if you do it like that. I agree with you. All right. You won. The author of this code. It's almost like this is why I like read other people's code. This is precisely why, because you sort of basically have an opportunity to look into how the author's head works. And what I'm arguing with right now, actually I'm arguing with the author of this code. And sometimes I win the argument in my head, and sometimes they win the argument. Like this time, okay, they won the argument. It's a little bit better like that, sure. So what basically I'm doing here, like I'm having a conversation with the author of this code. Am I crazy? But it feels like that, right? So basically, the medium of the conversation is the code, right? Not the words of the spoken language, but rather the code. We communicate with the code. So the author is trying to tell me something. I'm trying to comprehend it and seeing there's some problems. Sometimes there is no problems and stuff like that. It's just a medium for conversation, mate. Okay, everything seems to be compiling. All right. So next one. So we actually translated a big chunk of code. So the next one is a grid velocity update. So we need to iterate through num cells. What is a num cells? We're iterating through all of the grids and shit. Okay. And also, okay, I see what you're doing here. Yeah, again, if you had like a proper two-dimensional arrays that is straightened up in the memory, you could have written this code a little bit simpler. Yeah. So essentially you're iterating by index, and then you have to translate one-dimensional vectors to two-dimensional one. Yeah, classic. Okay, and num cells, do you actually pre-compute num cells anywhere? Yeah, num cells. Yeah, it's a grid size by grid size. Okay, I see. So in our case, we can actually do that a little bit simpler. I think we can simplify this entire code. So, and it's going to be something from gx. All right, gx is from 0 to gx less than grid resolution. So gx, here's that. And then, so instead of one, how to say that? One-dimensional, two-dimensional. I want to call it one-dimensional loop. Yeah, I think I can call it one-dimensional loop. Instead of one-dimensional loop, we can have two-dimensional loop. So for int gy grid res gy. All right. And so we can probably get the current cell. So the current cell is going to be cell grid gx and gy, right? Gx and gy. And so if the mass of this thing is greater than 0, we're going to do this kind of stuff. So we divide velocity by mass, and also have a boundary conditions, which is kind of interesting, I think. So we will be able to at least get rid of these 2 lines of code because we already have x and y. We already have them. Why do you need to have the second thinking here? Your condition is gonna fall through and it's gonna... Why do you need this thing in here? Seriously. Like, you don't need that. Like, it's... Oh my god. Seriously? Seriously? Okay, I'm gonna give the author benefit of doubt. Basically, originally the code was not like that, and it was just like in a rush or something, and it's sort of like a typo. It's like a slip through. But come on! Come on! Seriously. What the hell? Anyway, so I'm judging the author of this code, but not too much. Okay, because sometimes I make stupid mistakes, right? But I admit that they are mistakes. Anyways, so all right. This is fun. Holy shit! Even if it doesn't work at the end, I'm having a lot of fun right now for some reason. For no reason whatsoever. Like, it's just like whatever I do doesn't even work. So, oh, holy shit! I will have to translate all of that. Well, we probably don't need interaction though. I'm pretty sure we won't need any interaction, but maybe it would be nice to have it. But yeah. So though we already have all of the necessary tools to, you know, to translate this code a little bit faster. So Zozin, translate faster. Translate faster. Okay, I'm gonna translate this faster, just for you, chat. Just for you, imaginary chat in my head. Okay, so it's gonna be cell v vec2 div, and we're gonna be dividing it like that. All right, so we converted that thing. So the original thing is gonna be here. All right. Okay, let me see. Cell mass is vec2s. Okay, cool. So what about this one? So float 2, this one is just vec2. Gravity is going to be vec2s. Yeah. Wait, what? Ah, I'm an idiot. And then we're going to be actually adding this kind of stuff in here. So it's going to be vec2 add this thing to this thing. Oh boy. So, and then we're just multiplying this stuff like that, and maybe I can do vec2s. Right, it's gonna be just vec2 mult. And I'm gonna put it like that. Compile, doesn't compile. Because we don't have DT. Okay, I remember DT actually. DT is defined somewhere up there, if I'm not mistaken. Yeah. So we have to define it like 1, I suppose. We might as well also copy paste it like completely with a comment just in case. So there we go. So here's the gravity, and we don't have a gravity because we haven't snapped to reality yet. Okay. Const float dt, here it is. So here's our gravity. All right. Simulation. Let's simulate. You didn't miss anything? No, I'm still streaming. Almost done, I hope. Okay, Pog. All right. So simulate. What it was doing. Almost 4 hours. Okay. So now. Does it compile? Yeah, it does compile. I think. Gravity. Cool. We don't need that anymore. We can just do it like this. Yeah, so this is needed for the conditions and whatnot. For the conditions. So gx, but this is a resolution. gy resolution. There we go. Seems to be compiling. Cool. And then we are signing back, right? But we're gonna do that only once. Okay, we don't need to do it twice. There's no reason to do it twice, only once, because your condition is gonna fall through and everything's gonna be okay. To be fair, you don't even need to do it outside of the condition. You see what I mean? You can just do it like that. But maybe I'm missing the context. Like maybe in the context of when this was developed, it kind of makes sense, but now it doesn't make sense anymore. And you know, the usual jazz. But we're almost done, actually. We're almost done. Okay, so grid. It's not I, by the way. It's actually gx, gy. Gx, gy. Oh boy. All right, so the last huge chunk of code that needs to be translated in here. So we're iterating through all of the particles. So we converted particles to grid, we updated the grid velocities, and now we need to convert everything back to back champions of the grid. Okay. So we're taking this stuff. So this is going to be just a particle. By the way, do we save the particle back? Well, no, we save it to the grid. Okay, so that's everything's fine. So here's the particle, and the end of the loop we save the particle in here. Okay, that makes sense. That actually makes sense. Reset particle velocity, we calculate for scratch. Okay, so that makes sense, right? So, and here what we have to do is just vec to s0, ps particles. Okay, cool. And we set it to 0, everything's okay. Now I need to take the cell index, right? So I'm taking the cell index, and it's quite easy because it's a IVEC, the binding of IVEC, and it's just going to be IVEC2 from VEC2. Is it going to compile? Okay, again, I forgot to put these things in here. Okay. So it looks cool. Next is this one. Is it the same as above? I think it's literally the same as above. It's a px cell idx minus 0.5. Can I just copy paste this thing and see? Yeah, it's literally the same piece of code. Quadratic interpolation. Yeah, quadratic interpolation is literally the same piece of code. So okay, so maybe I can. How much is it the same? Well, yeah. Okay, that means I can copy paste this thing from there. So idx cell, including cell div though, right? Though I wish my brain worked a little bit better. And furthermore, I'm pretty sure I made a mistake somewhere there, so I'm copy pasting the mistake. But hopefully that will speed up this entire stuff just a little bit. If you know what I mean, right? So quadratic interpolation waits. It's literally the same piece of code, and then we're going through all of the like surrounding cells and whatnot, and we're just doing these things. All right, and everything seems to be okay. Maybe this thing could be actually extracted into its own function and whatnot, right? You know what I mean? So, all right. So here is the float B constructed affine particle momentum matrix from okay. I have a feeling that we won't need that. Yeah, I feel like we won't need that. So B. Oh shit. Okay. Okay. So this one is actually kind of like a term. Then you add it to B, and then B is going to be okay. So this is a complicated stuff. Like this is for like affine transformations and whatnot. Since we're not doing any of that, so we probably don't even need it. All right. So I'm gonna just assume that it's not needed. So this is a grid to particle, right? So it's a grid to particle. And in here, I'm just doing this like that, and there we go. So, and I actually wanted to make this thing like an integer, right? So then we consume the weights, right? We consume the weights. And this code reminds me something, yet again. It's actually very similar to what we had up there. And I have a feeling that maybe it's actually what it is. Can I just copy-paste this thing one more time and just confirm that it is the same piece of code? Almost. It's almost the same piece of code. Interesting. Okay, so but in here we actually take the index, but we don't need the index because we can access things directly. It's not needed at all. Anyway, I suppose I can just take the code that computes cell X, right? So, so I already have weights, right? And I just need cell X. Okay, where is cell X? Okay, so here is the cell X. Maybe I should actually keep cell X. Yeah, this is the original code. Here's the cell X, and now we need to compute an index, and there's distance, and it feels like it's a cell distance. Isn't this a cell distance, essentially? Right, wait a second. This is literally cell distance. It's just like the code is copy-pasted. The code is not only copy-pasted, but some of the variables are like changed. But maybe this thing like has a slightly different like semantic and whatnot. Yeah, essentially probably after that. And it even computes cell indexes, just does that in a different order. Like the code is copy-pasted and shuffled around. Ah! Physicists! What the hell is wrong with you? Stop copy-pasting code and shuffling it around. You're making my job difficult. Job security, by the way. Ah! Okay. Okay, so this is so goddamn funny. And we don't even compute the cell dist because, okay, so the cell dist is used in this term thing. Oh, we don't even need that. Okay, I see. I see. So we only need like a weighted velocity at this point, right? So we only need a weighted velocity right here. So, and it's based on the weight and whatnot. And what we need cell X for though? Cell X is needed for in. Okay, I see. So this is a weighted velocity. All right. So then we take a grid, a cell X, cell X, Y. All right. Then we take a weight, and then we get a weighted velocity, which is vec2. Right? It's a vec2 multiplication. We're multiplying this thing with vec2s. All right, it's a vec2s, and we have a weighted velocity. We have a weighted velocity. So and then we have to have this thing. Oh shit. Yeah. It's gonna be vec to add pv weighted velocity, and I think that's pretty much it. Okay, everything compiles. After that, we don't need that. Then we need to add vect particles. So then we clamp in everything, and we also have having a mouse interaction, but I think I'm not going to actually add a mouse interaction, at least for now. At least for now. Okay. So we're adding this stuff after the main loop over the grid and whatnot. Right, so we're adding this stuff in here. So it's going to be px, but in fact it's going to be vec to add px, then vec to multiply pv with this thing, which is vec to s. There we go. So we've got that going for us. And now we need to clamp this entire thing. So when we're clamping these two things, I guess we're clamping them component-wise, right? But I don't really know. Safety clamp to ensure particles don't exit simulation domain. Okay, sure. Sure enough. But I'm not sure how clamp works. So, where is the clamp? So Unity scripting. Clamp. Do we have a clamp in here? Maybe not. Unity clamp. I'm just afraid that maybe I can derive that information somehow here. So px. Oh, I see. So we're probably clamping the px, and this is lower one, and this is bigger one. Okay. So let's actually introduce something for clamping things around. So it's going to be vec2 clamp. So it's going to be vec2a, vec2 low, and vec2 high, right? So we need to do these kind of things. And let's just clump it. Let's just clump it. So this is going to be vec2 result. I'm not sure if it has to be like that, but anyway. So if a x is lower than lx, I do ax equal to lx. If x is higher than high x, I set high to x. So that's basically what we have in here. If it's lower than lower, don't allow that. If it's higher than higher, don't allow that either. And we can then copy paste this entire thing and query replace x with y, and then just return a. So that's the easiest way to actually achieve that. That's the easiest way to clamp things around. Okay. Now, so we added these things like that, and it's going to be vec2 clamp, right, and this one is going to be vec2 s. This one is going to be vec2 s, and I suppose we can just like use it like that because it's going to be converted more or less safely. So this is a big grid resolution, and it seems to be compiling. Okay, so we clamped everything. Mouse is not going to be there, and we need to assign particle back to back. Okay, so here's what we have in here. Here's what we have. So it's actually particles. Cool. Nice. We finished the simulation, and it's almost 4 hours. So now we need to hook up this simulation to the main loop and whatnot, right? So yeah. Translate npm start and npm simulate. Okay, I'm not gonna push that anywhere. So now if we call simulate, right, if we call simulate, so that's how we do that, right? So in each update, we just simulated the amount of iterations we have, iteration, and the amount of iterations is actually 1. So that means, according to this code, we just have to run this function once in update. That's what we need to do, I suppose. So we did that. right? Then we want to do something like npm simulate, right? We're simulating everything. And let's actually do the following thing. Let's actually run this entire thing and see if it like crashes or fails, or maybe, okay, everything seems to be okay. Does it consume too much resources on my machine? And it doesn't even consume that many resources, probably because it optimized the way or something. Who knows? Who knows? But I can always check that it's doing something, at least by going into the debugger. Right, so it's going to be ggdb. And of course, we compile this entire shit, and it's going to be just simply ggdb npm. And then I'm going to break on npm simulate, right? And then I'm going to run this entire thing, and I think it actually stopped, and it's doing things, right? It's doing things. It's, you know, filling up the grids and stuff like that. Everything is just going, so it's doing things, which is cool. All right, now after we simulate it, I think what we want to do in here, we want to actually iterate through all of the vertices. I think I mean particles. So, and we're going to do it like this: size t I0 particles, I think it's count plus I, and for each particle we're going to be actually adding the particle position as the vertex, and we're going to render that. To be fair, I have an interesting idea actually. Let's actually render their positions and see what's the domain, right? Will we be able to even see them? Because who fucking knows? I don't know, maybe we won't. So let's printf them. So it's going to be something like printf vec2 is going to be f, and it's going to be particles I x, particles I y. And after we printed it once, let's actually crash the whole applications, because we don't really want to spam the output too much. Right, let's not spam the output too much. So this one is not f, is that what it's trying to tell us? Okay, x, y, thank you so much, very cool. Okay, so here are the positions, and they are around, like, we should be able to see something, right? Because our resolution is minus width plus width minus height plus height, and the resolution is 800 pixels by 600 pixels. So if it's within like small rectangle, we'll be able to see at least something, right? We'll see it like small thing just moving around or whatnot. So let's actually now clamp this entire thing to three vertices, right? So we now have 3 of them, and let's actually try to simulate it and see if they're updating their positions on each step of the simulation and how they're updating their positions. Okay, so all right, they're moved around, and there they jump like to here, and they sort of settled like a, that's a very interesting. So it yeah, so these particular particles sort of kept teleporting or something. But it settled around like the edge of the grid anyway, so that's what it feels like. And we're also clamping around, so maybe there's something wrong in here, but in any case, we can try to now render them and see if they're doing something interesting. And regardless of the outcome, I'm finishing the stream, right? I'm finishing the stream because I'm already streaming for like 4 hours. Yeah, I just want to see something interesting, right? So I want to see something moving, and we'll see if it's gonna move or not. So we have to set the position. So this is gonna be X, this is gonna be Y, and we're gonna use the red color. Right? We're gonna use the red color. Okay, and we're gonna simulate all of them, right? Particles count. Well, that was very fast, but it did something. Okay, let's actually make the size of the particles a little bit smaller. Let's actually make it 1 pixel, and I think it was too fast, and it's sort of like clamped into. I don't even know, man. I don't even know. Okay, so what if we change the DT to something smaller, right? Half of it, and actually like make it like very, very slow. It's still too fast. It's still too fast. Huh. Even smaller than that? Huh. Maybe it doesn't go very, very fast. Alright, so maybe I'm going to actually make the size of this thing a little bit bigger. Maybe not. Did it recompile anything? Oh yeah, I see. So I should have not done it like that. So the original size is going to stay the same, but when I set the resolution, I'm actually going to divide it by 10, so it will, the shader will think that the screen is smaller. That's basically the idea. We're going to try to trick the shader. And it didn't really work the way I wanted it to work, but okay. Here's another thing. We can try to multiply the positions by 10. So maybe that will make it make them look a little bit more interesting. But yeah, don't really see much, and it doesn't really slow down. That's the problem. Yeah, it's just like poof, pee poofs. Maybe we have to delay. Yeah, how do you delay? So let's do like use sleep or something. Use sleep. So this is microseconds, we divided by 60 for 60 FPS and whatnot, and then we are including unistd h, and of course we want to do something like that, and implicit declaration of use sleep. It's just like disappears. It's kind of funny how it just disappears, but it's doing something. That's what's interesting. It's doing something. What if we make like a bigger grid? 128. What about 128? Okay. Grid. 256. It is doing things, I think. 12. Huh. Wait a second. How do we do the particles? So we boxes by this. Why there's so little particles? Why don't we have enough particles? Wait a second. Printf. How many particles did we got? Particles count. How do we have? How many of them? It's still 256. Oh, essentially, I see what it's trying to do. Yeah, I see what it's trying to do. So essentially, it actually generates a small box within the whole domain, so it can like flow around or whatnot. Yeah. So maybe if we make the box a little bit bigger, maybe that will do something. But it just, you know, flows away. And on top of that, I think there's some problem with the coordinates and whatnot, but I don't know. So 16, what was 32? 64. It doesn't make it bigger. Box doesn't make it bigger. Actually, it asserted. Okay. So we have not enough particles, not enough vertex capacity. Okay, let's make it like 8. So let's allocate more vertices for this kind of stuff. That's what we got so far. We got sort of like a triangle that just plumes away. and I cannot make it, you know, slower for some reason. So maybe I can even make it like that. Well, it kind of makes it slower, I guess. I can make DT like, yeah. I wish I could like zoom it in somehow, but that means I'll have to change the way we translate the coordinates, right? So that's what we need to do. So right now, I think we're trying to translate UV coordinates to like -1 and 1. Maybe this is not what I should do. Right, maybe this is not what I should do. What should I do instead is maybe just leave it as it is. All right, just leave that shit as it is. And when I translate it screen to NDC, right, so the entire position, right, I have to take the position in the screen coordinates and I have to subtract, I'm pretty sure, I have to subtract half of the resolution, right? It's going to be half of the resolution. All right, so I shifted away a little bit. Then I divide it by half of the resolution, right? I divide by half of the resolution, and I think that's essentially what I'm doing. Yeah. So it's from 0 to the full resolution, half of the resolution, divided by half of the resolution, minus 1, 1. I think that's basically what we need to do in here. Looks way better, not gonna lie. Yeah. Let me try to give it more particles and whatnot. So what if it's gonna be like 128 by 128? And it's still not enough particles. So what about 16,000 particles? Holy shit. I think we've got something. We can try to change the resolution 20 by this. Maybe that will give us some zoomage. It didn't really do anything, right? Yeah. It's pretty slow, but we got something. I'm pretty sure I made a mistake somewhere while translating all of that, but we got something within 4 hours, and I know nothing about physics and simulations and stuff like that. I know a little bit of programming, a little bit of math, but yeah. So I guess it's kind of cool. So something with you sleep. Let me try to. Yeah, I remember that for you sleep, you have to include something like POSIX, something. All right. You have to put X open source. Maybe not. Is that what you have to do? I think that's what you have to do. Find this thing to be 5,000. And yeah, okay, and it works relatively fast. It's a little bit laggy. It's still a little bit laggy, but it works relatively fast even on my potato PC, which is cool, I guess. All right, so hook up the simulation to the event loop. Right, and let's actually now create the, so I'm gonna start this repo. I think it's a pretty cool repo. Let me see, it's gonna be Zozin. So npm OpenGL. So it's going to be readme. An attempt of a dumb software engineer to implement something that resembles the material point method. Okay. It's going to be public. Create repository. And let's actually do that. Yes. Add origin. And okay. I'm going to push that right into the repo. And this entire thing is available for everyone. So I'm gonna actually put this thing into the description, right? So my source code, here it is. So we spent 4 hours doing that. That was fun. We get something, I suppose. That was interesting, at least. At least for me. I don't know if it was for you. Let me know in the comments below if it was interesting for you. But unfortunately, boys and girls, it is time for me to go. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow, according to Skidoodle, we're doing game development in OpenGL. We are going to continue developing our game that looks something like this, right? It uses OpenGL and stuff like that. It's in C++. And yeah, smash like, subscribe, hit the bell, and I gotta go. That was fun. Love you. Mwah.